Hello, guys. Can you hear me? Yep. Okay. You're muted, by the way.
Okay, that's us good to go. Welcome everyone to PocketQube Workshop. We're now live and we're opening. This is our usual PocketQube Developers Workshop, which is for PocketQube, for people to understand what PICO satellites are and their applications. Our first speaker, we've got Julian Fernandez from FOSSASAT. Can you hear me? So if Julian would like to start his presentation. You're muted, by the way. Okay, that sounds good to go. Welcome everyone to PocketQube Workshop. We're now live and we're opening.
Okay, so do you want me to start?
Yeah, go for it.
Okay, perfect. Then let me just share my screen. 1 second. Okay, great. So let's see if my screen is visible. I think that should be good. So sorry for the delay. I think we're a couple minutes late. Or are we on time? Might be on time.
We're on time. We should be good.
Okay, great. Then welcome everyone to the PocketQube workshop. I mean, it's great to be the first speaker in this lineup of great talks. We've got some really interesting content coming up today. For those of you that don't know me, my name is Julian Fernandez. I'm the CEO and co-founder of FOSSASAT, which is a company dedicated to the development of PocketQubes. So most of you probably already know FOSSA from our last mission, FOSSASAT-1. But anyways, I'll still do the typical introduction for those of you that are new around here and that don't know this small community. I tend to say this a lot. PocketQube community is tiny. We're probably 100 or 150 people worldwide. So in the end, most of us already know each other. So as I was saying, FOSSASAT is dedicated to developing PICO satellites. We work with the PocketQube form factor. And we've recently launched a mission on an ALBA pod cluster in 2019, the FOSSASAT-1. Actually, this time last year, we were presenting our FOSSASAT-1 project, and now we have the results. We've launched it into space, and we're able to explain the results now in this presentation. So the goal of this presentation is going to, very briefly, since we have limited time, and excuse if I go over things a bit too quickly, go over the results and go over the timeline of events for the future of FOSSASAT. So we'll be going over the FOSSASAT-1 mission and results, the PICOBUS mission, which is due to launch in the next couple of months, with the FOSSASAT-2 and FOSSASAT-1B satellites, as well as our new PocketPod deployer, which is aimed at giving, well, low-cost access to LEO services, and our latest generation FOSSASAT-2E satellite. So a bit of introduction on FOSSASAT. We were founded in 2018 as a non-profit student association, and we were founded based off a series of events online, a bit following the PocketQube community. We met on Reddit as a group of students and individuals, and we decided to launch a satellite into space. So I think FOSSASAT-1 is a great success story as to how just a bunch of students got together and managed to, well, launch a satellite into space with little to no funds available. And I'm just really realizing now, I think the presentation is not being seen in full screen. So I think we're gonna have to continue like this, but excuse the fact that the presentation is on full screen. So we've already launched a satellite into low Earth orbit, FOSSASAT-1, which was designed as an open source project and is able to be, well, seen online on GitHub. And actually, there's quite a lot of universities and individuals which are using it as inspiration for PocketQube launches. And we also designed the FOSSASAT-2 and 1B satellites, and now we're advancing as a company. So we recently got established as a corporate entity. So we're starting to deliver commercial services both in low Earth orbit launch brokerage. So that is with our PocketPod deployer for PocketQubes, and satellite bus and satellite platforms services. So that is putting a platform in space for a client to have their hosted payload on board the platform at a very low cost. So FOSSASAT-1, as I was saying, started development in 2018. It was a bit of our first steps in the PocketQube community. So we were still learning about how PocketQubes worked. We wanted to demonstrate an Internet of Things payload in space dedicated to LoRa telecommunications. And as you can see in the pictures, it's a 1P satellite with deployable solar panels. So it was actually, back in the day, the smallest PocketQube, well, I think the smallest satellite in the world to have deployable solar panels. A bit more on how that went in the next slide. But this satellite was meant to create an Internet of Things network in space. So back in 2019, we launched the FOSSASAT-1 into space. You can see here the picture of myself in the clean room during manufacturing, and then during integration. And thankfully, well, we were able to launch it successfully into space. And well, our first PocketQube project, we didn't really know what to expect. It's quite a task to launch a satellite into space without any previous experience. And as a student group, it was quite a daunting task to launch this into space on various levels, due to legislation, due to funds, due to technological development, etc. But in the end, we actually achieved it. In fact, most of you will probably know this from Twitter. We're quite active on Twitter with regards to our updates on our satellites, and there was quite a bit of attention on the FOSSAT-1 satellite due to the fact there was so much international involvement. In fact, since the first day that we launched it on the AlbaPod, well, it flew on an Electron rocket. An Electron rocket from Rocket Labs. We had a lot of individuals, especially amateurs, listening to the satellite to hear these first signals. And in fact, an hour or two after the separation from the deployer, we got our first RTTY signals. So for us, this was already a huge achievement. It was a first, to be honest. I don't think it was something that had been done before in this way. So we were very happy to have received the first RTTY signals from the satellite. However, not everything went exactly according to plan. What you can see here in these slides are two RTTY signals from a station in, I believe this is the Czech Republic, and China. We actually had some amateurs in China which were involved in receiving packets from the satellite. And unfortunately, due to an issue in one of our burn wire mechanisms, we were not able to deploy the solar panels and antenna completely. So we had a limited performance on the emissions coming off the FOSSASAT-1 satellite. Due to this, we actually had to hand decode some of the initials RTTY packets from the satellite. So this is one of the points which I wanted to give on this presentation. And it's just how important it is to have redundant transmission protocols. The IRU insists on this. In fact, they were quite skeptical on LoRa. And they wanted us to use a redundant ham amateur-oriented protocol. So that's why we integrated RTTY. And in the end, we actually received about half of our total packets on RTTY, and it allowed us to decode very, very low power packets at incredible ranges. So that's one interesting consideration which we learned of the FOSSASAT-1 mission. And we also managed to test LoRa successfully. We managed to decode packets from the satellite, and we managed to demonstrate that LoRa transmission and reception from space was actually possible. Also, with the involvement of the amateur community, some users were able to record SDR packets with an SDR packets off of the satellite and then decode them on Earth. So regarding the actual results which we got, besides the functionality and proving the bus, we were also able to get thermal data off of the satellite. And excuse 1 second, cat is on the keyboard. Back to what I was saying. Regarding the actual data, we got a lot of thermal information of the performance of the satellite. And we were working with a company called Radiant Systems, which carried out the thermal analysis of the FOSSASAT-1 satellite. And in that regards, well, we have some articles published online, and we were able to see that the temperature ranges of a 1P satellite are actually quite limited. In fact, we're seeing a variation of our battery from around -5 to 15 degrees, and we were quite surprised by this, considering we had initially considered the need for resistive heating for our satellite. And then externally, we were hitting ranges from -25 to around 50 degrees. Regarding the EPS performance of our satellite, there's some results here regarding our battery performance and our temperatures. I won't go over exactly what we found, considering there's a report which will soon be published, which goes fully in detail over what we learned for the FOSSASAT-1 mission. However, we did see that linking the thermal model to the EPS was very important, since low temperatures had quite a large influence on our satellite battery, and that testing and standardized procedures are imperative to having a successful mission. So FOSSASAT-1 was a success. It worked for 3 months. You could consider it a partial success because we didn't achieve our full operating lifetime and we didn't deploy our antenna completely. However, we were still able to achieve probably 70 to 80% of the mission objectives which we had established. Regarding our next missions, one thing which we're working on since already the launch of the FOSSASAT-1 mission was the PICOBUS cluster, which we're launching on the Firefly Alpha rocket in the following months. So this is a collaborative project which we took on, and we actually got, well, the prime contract for, even though it was a free launch opportunity on a maiden flight from Firefly on their Alpha rocket. So we're still pending to see how that goes. And LibreSpace developed an 8P deployer for this project, while we flew the FOSSASAT-1B and FOSSASAT-2 satellites. AMSAT flew their Genesis N and Genesis L satellites, and LibreSpace flew their cubic satellites. So it was a bit of a very big experimental launch, which we were carrying out to test lots of technologies, including, for example, a collaboration between AMSAT, Applied Ion Systems, and FOSSA Systems to test a pulsed plasma thruster in space. So the FOSSAT-2 and 1B are the next iteration satellites from the FOSSAT-1, which are obviously the FOSSAT-2 in a different form factor. It includes a new GNSS experiment by the European Space Agency, a camera, a full magnet worker ADCS, and we have a LoRa repeater, as well as having moved over to the STM32 architecture. While the FOSSAT-1B has an updated burn wire system, updated internal electronics, and a LoRa repeater. So these are the satellites which we'll be launching in the next couple of months from Vandenberg. So after having launched the FOSSAT-1 and the FOSSAT-2 and 1B, well, which are pending to launch, we discovered that there was this lack of launch opportunities for PocketQubes in the market. Right now we have Gauss and Alba Orbital. However, considering the increased size of the PocketQube in the last couple of months, we considered that it was necessary to fill this gap to increase the launch opportunities of PocketQubes to low Earth orbit. So this is why we developed the PocketPod, which is an 8P deployer using a high reliability pin puller developed by Deployables Cubed, which will actually be giving a talk here in a couple of hours. And what we're trying to do with this is reduce costs to access space. So the launch cost for a 1P is 18,000 euros. We offer discounts for educational and nonprofit missions, and we're also able to offer testing services for companies and educational institutes so that they can test their satellites at our facilities. We work closely with the National Aerospace Institute of Spain, so we have TVAC, SRS shock, and vibration table testing facilities, which we can offer together with the launch. So our first cluster will be launching in April of 2021. 9 satellites will be launched, and we have 5 customers on that mission. And there's an ICD available, which should be online soon, as well as you can contact me through email to discuss if you're interested on the payloads user guide regarding the levels or the ICD. We're using a PocketQube XL envelope, so it's fully backwards compatible with the Alba pod. And we're also able to mount the pod in a vertical position. So we're able to better optimize space on, for example, this is the Momentous Vigoride platform, which we'll be flying in April, and lower costs. So our planned launches are April 2021, Q3 2021, and Q1 2022. And we have a configurable orbit of between 450 and 550 kilometers. So our clients are also able to have some decision as to where they're being placed. So here are our constituents. We're flying the FOSSASAT-1, the Challenger by PICOBUS, which is a 3P Earth observation payload. And we're flying the Canary Hatchling by Weather Technologies, which will be testing the actual platform, the satellite bus. And in the future, we'll be testing radars, as well as 3 FOSSASAT-2 platforms, of which 2 are carrying missions by PorkChop, which is an experimental pulsed vacuum arc thruster, and a Sea Shark satellite, which will be testing IoT services in space. So regarding the FOSSAT-2E, which will be launching in April on this initial mission, here are just some main characteristics of the satellite. However, I would like to say that there is an infographic on our Twitter and on the exhibitors page for FOSSA Systems, where you can see more information regarding the satellite. We also have an ICD available for payloads where they can see our standardized space. But just going over the main specs, we're talking about 1P payload space. We have up to 9 watts of power, a downlink of up to 0.25 megabits per second. And most importantly, we have a cost of 100,000 euros, including launch into low Earth orbit. So quite competitive compared to the current solutions. And to our understanding, it is the most, the least expensive platform currently available in the world for satellite payloads. Excuse the speed at which I went over all of this information. There was a bit of limited time for all the topics which we had to cover, but I'm available online through Twitter or through my personal email. My colleague Vicente Gonzalez will be giving a talk in a couple of hours, I think just after the lunch break, and he'll be discussing the FOSSASAT-2E platform and our PocketQube launch services in more detail. So if you're interested, you can also attend that session. So I think we can go for the questions if there's time. Kais, if he's online, I'm not sure.
Right, thanks, Julian. That was a very good, informative talk. Next up, we've got Ben Cartwright from PocketQube. We are developing another 1P project. So we're waiting for him to come online.
Okay. If you want, I think there's a question in the chat from Powell.
Yeah, feel free.
Okay, so Powell asks, why would the satellite stop working after those 3 months? The issue we had with FOSSASAT-1 satellite was that our solar panels did not open. So we had limited power compared to our estimated power budgets, where we were expecting around 600 milliwatts, and we ended up having around 100 milliwatts. Added to the fact that our thermal model was not perfectly linked to our EPS, in such a way that our battery slowly degraded its performance to the point where it didn't have enough power to sustain transmission. In fact, the life of the satellite is longer than that. We suspect that the satellite operated for around 6 months. The issue is under 3.8 volts. We had a low power setting, which would transmit at 10 milliwatts instead of 100. And since our antenna had not opened, we weren't able to decode these packets successfully. So we suspect the satellite lived for longer. However, we only managed to decode packets during those first 3 months of operations, which in the end was enough to give us several, I'm not sure if it reaches the thousands, but hundreds of data points, which we were able to analyze. And in the chat from Zoom, elaborating on LoRa performance, we're able to say right now we're still studying all our information. However, we will be using LoRa for our IoT constellation, which my colleague Vicente will be talking about later. And LoRa, I think, has successfully proven itself as being able to achieve communication from LEO. One thing to consider, though, is that LoRa is a proprietary modulation, and we did have some issues in understanding exactly how LoRa worked, since not everything is explained in the data sheets. And in practice, we did have to make some modifications to the satellite firmware while it was in orbit. So we had to change some of the characteristics like the sync word. We had a couple of issues, but in the end, we got LoRa to work. We're relatively happy with it, and we think it has a lot of future for enabling IoT telecommunications. Great, then I think that's it, Caius. Then I think we can go over to Ben Cartwright. Best of luck to him. Thanks.
That's good. Good talk. Hey Ben, are you all okay?
Hello, I can hear you, but I'm not able to share my screen at the moment. I'm not sure what's going on. Can you hear me?
Are you able to share your screen now?
I have no button for that. Hang on, let me leave and rejoin because it wasn't letting me do anything earlier.
Okay.
So I don't have any of the host permissions.
Okay, 2 seconds. I'm going to email you another.
Yeah, please.
Amon.
Hey folks, just trying to get Ben set up here. So yeah, thanks for the first talk, Julian. It's really useful to hear your developments, and it's great to see you guys progressing after launch last year with us. And yeah, we've got quite a busy schedule today. We've got some people talking, so it's all going to be quite rapid fire, hopefully from now on. And yeah, it's a bit weird not having everyone in Glasgow, to be honest. But hopefully this will be the best stand-in we can do. And yeah, it's a big new world with this COVID virus, unfortunately. So yeah, if you just bear with us, we're trying to get Ben set up. Yeah, I've got it. So let's just turn on actually. Huh? Yeah, get Alice. After Ben is Alessandra from TU Delft. She's in the chat just now, so we'll have her scheduled up to do her talk if she's okay with this.
Yes, I'm okay with it.
Okay, good. So feel free to start your talk.
Okay, so let me share my screen. I hope it works. Yes. Can you see it? Yes. Okay. Okay, great. So good morning, everyone. It's a great pleasure to be here today to speak about our Delphi PQ PocketQube. Actually, it is a pity that we couldn't see each other in person like last year. I really enjoyed the last year workshop because I think it's very important to stay connected as a community. But okay, we'll do it online and it will be fine. For those that don't know us, I don't think there are many out there, but we are from TU Delft, Dutch university, one of the 4 technical universities, which is composed by 8 faculties. And just to give you an idea about how big we are not extremely huge university compared to some universities in UK, but we have around 24,000 students last year. We are from aerospace engineering faculty, so one of the 8 faculties of TU Delft, and we are very international oriented faculty because we have a full English taught program and we have about 47% of our international students did these flat weights. But my group is from a section of the Department of Aerospace Engineering, and this is a space system engineering. We are not a very large group. We are 12 scientific and staff members, and we have 12 PhDs at the moment working on different projects. Our key projects were the Delphi NATO satellites, Delphi C3 and Delphi Next, and now we're busy with the Delphi PQ. We cover a broad range of expertise, in general nano and microsatellite engineering, distributed space systems, navigation, propulsion, in general system engineering, miniaturized instrumentation, and radiation effects assurance. The expertise on space engineering and space-related research is not only happening at the aerospace engineering faculty, but there are groups across the university in different faculties. And for this reason, it was created the Delft Space Institute back in 2015, which is bringing together people from TU Delft, but in different faculties. We have 3 main focal themes: sensing from space, distributed space systems, and space robotics. And the Delft Space Institute was really supportive during the development of Delphi PQ. So we are very grateful for the support. In-house, we have some facilities to build satellites, clean room that was used for our CubeSats before, and we are very happy that finally we got to use it again for Delphi PQ. So you can see Stefan and Chefcat, the last testing of the satellite that happened last week. And of course, Chefcat is the contact point if you're interested in knowing more about our clean room and the activities can be performed there. We also have a TU Delft ground station, which is situated on top of a very high building of electrical engineering. This is 90 meters high, and it is equipped with multiple antennas, which we and VHF and spend for downlink. And this is run in collaboration with ISIS, the company close by that is developing CubeSats. Contact point is Stefano Speretta. So the Delphi space program in general has as an objective hands-on education. We are a university, so we are really interested in train our students with hands-on projects. But we are also focusing on miniaturized technologies. So we believe that the future in space miniaturization. And we provide end-to-end engineering for very small satellites. So as I mentioned, we have a past in CubeSats. We have developed two CubeSats, Delphi C3 launched in 2008 and Delphi Next launched in 2013. Delphi C3 is still operational, so it's still giving signs of life, while unfortunately Delphi Next had a failure only after 3 months after launch. And now we are developing Delphi PQ. We are very proud that we are going to deliver it to ALBA tomorrow. So Delphi PQ team is composed by Stefano Speretta. He is our communication engineer, but it was promoted to system engineer because in the last weeks he did everything to make the satellite ready for launch. Then we have a Chef Cat, our electronic engineer. He also did everything from mechanical engineering to soldering. Again, very, very important member of our team. And then Casper, it was a previous student of us, and he provided the software development for Delphi PQ. And myself and Ebra were just the project managers. We had some very interesting collaboration with the Dutch industry, which is of course very appreciated by the university because we are a public university. And we had a great support from Airbus. They helped us with the solar panels of Delphi PQ. Stellar Space Industry provided the structure of the satellite. GTM was also very helpful in helping us with the vibration test, providing the adapter. As Space, we collaborate on administrative things like the insurance of the satellite that are also important, and the ground station, of course, and Thales, where we performed the vibration test last week. So the Delphi PQ is a 3P PocketQube. You probably know about it, but yeah, this is the end design that we finalized finally. And Stefano will give a talk dedicated on all the details about the design of Delphi PQ. So here I just want to give you a very, very quick overview of what's inside our satellite. We have a EPS, which is composed by body-mounted solar panels. So we don't have deployable solar panels like FOSSA. We decided to go for body-mounted solar panels. We have the communication system. The onboard computer is based on SP432 microcontroller. We have an ADC system composed by 3 magneto-torquers and 1 MIU. And also we placed the 4 laser retroreflectors on the satellite in order to be tracked from ground in an easier way. And we are ready for launch in December 2020 with the cluster 3 of ALBA Orbital. Thanks a lot, ALBA, for giving us this opportunity. We were really hoping to fly soon our satellite. Now, we performed, in my opinion, a very important analysis on the orbital lifetime of our satellite that was done by Jasper Baumeister, the previous project manager of the FTPQ. There's a paper published on this, so if you are interested, please have a look at it. It's very interesting, and it's also a very hot topic, mitigation of debris in our community. So the study was performed with different assumptions. We looked, Jasper mainly looked at different mass over area ratios and different scenarios. And now we performed the simulation with Rama based on the information that we got about the orbit we will be deployed to from Momentus. So last week we managed to go to a vibration test facility in Holland, quite far away from Delft. It was a long drive, but we were very happy because due to the COVID-19 situation, facilities are closed, and it was really difficult to get access to this facility. But we managed, and you can see Delphi PQ mounted on the vibration table, and everything went fine. So we are very happy that this was done. So now conclusions. Despite all the difficulties that we had during the COVID-19 pandemic, we had to work from home a lot. You can see Stefan and Shevket enjoying the last testing of the satellite at home. And we had the delays in procuring components. It was really a nightmare. We had really many problems, but we managed, and we are ready for integrating Delphi PQ with the Alba Orbital Pod tomorrow. Shevket is there in Glasgow, so he will be participating to the integration. And we are really excited to be launched in December 2020. In the future, what we want to do is to demonstrate PocketQube's inter-satellite communication in order to implement distributed sensing systems. And this could be GPS, GNSS sensors, and radiation sensors. There is a small group in our group that is researching on micropropulsion. So we hope that in the near future, we will be able to demonstrate also micropropulsion for PocketQubes. And we are really looking forward for a closer collaboration with the other PocketQube teams. I think it was great to stay in touch, but I would like to see this more for the future launches so that we can share, for example, environmental tests and other experiences. So that was it. Thank you very much for your attention. And you can email, you can have a look at our webpage or follow us on Twitter. I'm happy if there is any question.
Hi all.
Hi.
Great presentation. Can't wait to launch your satellite with Alba. That'll be great. So Ben, are you ready to go?
Yes. Hello.
Hi.
Can you hear me?
Yeah, we can hear you all good.
Excellent.
Are you able to share your screen?
Yes, as soon as it's released.
Fantastic. Alessandra.
Yes.
I think you may need to get off from the panelist.
Yes, yeah, now I found it. Sorry, I have two screens and sometimes
Right.
I lose. Yeah, thank you.
If I share this, hopefully you guys can see the full screen presentation.
Oh, good.
Okay, so my name is Ben Cartwright. I'm going to talk a little bit about some different PocketQube platform concepts that I've been working on over the last couple of years. A couple of brief disclaimers before we start. This talk isn't particularly long, so there will be some time for Q&As afterwards. And the other point is that this is largely to show off some largely kind of phase A designs. Nothing here is really EM, FM hardware. So a lot of this is try to promote discussion and to try and to progress PocketQube platforms into more capable kind of versions of what they are now. I'm here representing two organizations today. One is the Flame Trench, and the other one is my own company, Citadel Space Systems, and we'll talk a bit more about both of those in a minute. Next slide. So a bit about me. I'm a spacecraft electronics and systems engineer at RAL Space in the UK. I've been there for a little over 3 years now, mostly working on space telescope hardware, so scientific cameras and high reliability instruments. I'm also one of the PocketQube engineers at the Flame Trench, and I will talk a bit more about what Flame Trench is in a second. And then last year, I founded with Julian from the first talk, a company called Citadel Space Systems, who largely focus on nanosatellites designed specifically for high reliability science, either in low Earth orbit or deep space. And I have fingers in a few other pies in the space industry as well. So a bit about the Flame Trench. Largely this came about from Twitter while I was still a student. And it was largely from networking with a bunch of British and American students and professionals in the space industry and makers and this kind of thing. And it became a really diverse group of engineers and scientists and students and people who were teaching and content creators and people doing STEM communication. And the Flame Trench really started as a way that we could kind of share what we were working on and show off some of our own personal portfolios and kind of have all that in one place and help each other network and grow in the industry. And that kind of evolved into us working on a couple of flagship projects together, one of which is TFT-Cube, which is our little PocketQube satellite. A couple of the other ones we have GAZE, which is a robotic observatory, which we're using to do amateur astrophotography and citizen science. And something we've started working on recently is Proxima, which is an open source imager for astronomy, which we're kind of building in tandem with GAZE. We're mostly crowdfunded, so our Patreon is linked there, and as well as our website and social medias. So a bit of the context behind the TFT-Cube project. One of our members, Joe Hinchliffe, is fairly prominent in the PQ community, and he's a fairly prominent maker as well. And he used to start working on some of these little PocketQube chassis designs, and he had a few versions of these over the last couple of years. And through him and his work with another organization, the Flame Trench had a bit of an opportunity to potentially fly a very cheap PocketQube mission through a CubeSat deployer. And so our plan kind of was, well, we've got a lot of people who are very talented students and makers. Can we build a PocketQube that is not just a really, really basic satellite, but can we do that on the cheap? So we tried to do that, and we had some success, and I'll talk a bit more about where we got to in a minute. So we wanted to do something a bit different from a very, very basic Arduino type computer and a radio module. So the idea I had was, when I was looking at rocket avionics systems in model rockets, a lot of the thrust vector control stuff and more advanced flight computers has really blown up in the rocket space recently. And so I was looking at a design kind of like this on the right here, where you have 5 sections of rigid flex PCB, and you can connect those all up in one piece, and it kind of makes all of your electronic systems much more compact, but you can fit a lot of electronics in a single space. And the idea I had was to fit a battery in the middle here, so you can fit all of this rocket avionics in one really compact space. And well, that kind of applies really well to PocketQubes, actually. And so we came up with a few concepts and really tried to refine this and make it a way so we could really minimize, in particular, the size and weight. Swap is size, weight, and power. Doesn't really help you optimize power much, but it really helps with getting the size and the weight down. And the result is that you can fit a lot more of your PocketQube electronics into one particular volume. So this was kind of our very initial concepts a couple of years back. And here, so you can see inside we have the kind of the basic stack that you get from regular PocketQube electronics. Top mounted antenna. These solar panels don't actually deploy, so it's kind of just exploded for viewing inside. And so you have this key 5-panel rigid flex PCB with all of your solar panels mounted on the outside, and your regular PocketQube systems are on the internal stack. At this point, the key takeaway is that this rigid flex assembly is completely structural. In a lot of other PocketQubes, you'll see they have a base plate, but they have some other kind of mechanical thing at the top. We don't have that. We just have a kind of stack through assembly. And the side panels here do a lot of the structural work in kind of making this all a rigid structure. So this is kind of like the start of the concept, and we sort of evolved this over the next year. So a brief bit about kind of standard PQ hardware. A lot of PocketQubes at the moment are completely implemented in their central stack. All of the OBC, comms, power units, all of your attitude, control, and electronics is all in the central stack. This is from FOSSASAT-1. Thank you, Julian. So the key thing here is that the PCBs are often still used for the walls because that's a really cheap and easy way of having integrated solar panels, but they only ever actually have PV hardware in. Occasionally you see they have a little bit of sensing stuff on the back maybe, but nothing significant. What we did was we took all of those sort of platform systems and we put as many of those as possible on the inside of the rigid flex kind of shell. So this is the second iteration. We're working on a third at the moment. So the key takeaway for us is that both your comms and your power systems are all on the inside of this rigid flex structure. So comms in particular go on the back of side here where you've got your solar panels mounted, and they also kind of go on this top side on the inside here, and there's a rigid flex connection that keeps them all nice and neat. There's each other solar panel has its power mounted on the back as well. So things like your protection diodes, your power optimization circuitry and stuff like that, maximum power point tracking, all of that is on the internal side of this solar panel. And actually the only thing we had on the internal stack was our OBC setup, and that actually gave us a lot more space to have a particularly complex onboard computer with external memory, external MRAM, to try to heighten the reliability of the system. The nice thing about this is on the inside, you can sandwich your battery in between some of your radio, your comms tech, and your OBC, and that helps keep the battery warm naturally. And what we do is we have SAMTEP connectors between the inside of the top side of the PocketQube and this internal PCB here, and that connects the two systems up. So we have like quite a dense, low profile connector to join those two up. You can see the results of this, of moving all of these stack systems onto the actual shell itself, is that you end up with a particularly large payload area in comparison to most of a 1P PocketQubes. So if you go back to this is kind of all your platform and maybe one board for your comms payload. Here you have pretty much 2/3 of the internal volume exclusively for payload electronics and hardware. So this is kind of one of the key benefits of a system like this. The other thing we built in was GPS. So we had an extra board mounted on the bottom of the base plate here with your GPS antenna. And if I go to the next slide, you can kind of see how we connected that up. So if you think about the internal PCB here, we have a high density connector connecting the rigid flex shell to the internal PCB. That kind of doesn't work if you want to connect anything to this extra PCB on the bottom. So we built up this flexible harnessing, which is actually used quite a lot in industry for particularly dense instruments and things like that. So we're making use of extra SAMTEC rigid flex connectors to link all that up, and it makes this kind of really flexible as to what you can mount on different PCBs or different parts on the bottom of the base plate. You can kind of chop and change depending on what your payload is. You don't have to have solar panels on this side, for instance. You can have a cutaway and have an observation payload and that kind of thing. It's very, very flexible. So what we're planning on doing with this is opening it up to students, either in Britain or in the US, because that's mostly where the flame trench tends to work. And we will open up a tender for students to fly an experiment on TFT-Cube, and we will help them with engineering support and building it up. And the idea is to kind of turn this into a sort of STEM communication and outreach project. It's only possible with the continued crowdfunding that we've been very lucky to have for the last 2 years. But likely with the amount of work it is taking to kind of get a more difficult concept like this to fruition, we were looking to start to open this up to the community, and we'll hopefully have some more details about what that looks like soon. So yeah, so that's where we are with that. A bit of the progress here. So we're working very heavily on the structural models because this is quite a unique assembly from a lot of what else I've seen and people working on. So this is the second iteration. We're working on a third at the moment to try to simplify some of this. I've got it here if you can see what I've got in my hand. So here's our structural model. You can see it's very, very small. I apologize. Inside, all of this volume in here is available for payload. And the rest of it is platform systems. But because of all that is mounted on the rigid flex, it's very, very compact. So we're prototyping GPS and radio in the US at the moment. We're using OpenLST by Planet Labs, although one of the parts is now end of life, so we're having to kind of rebuild it a bit, which is a bit annoying. But once it has been rebuilt, we will re-open source it, and everyone will have an updated, more current version of OpenLST. One of the cons of this kind of setup is that this 5-piece rigid flex assembly is absolutely not cheap. You're looking at a couple of £1,000 for a production run potentially, compared to a 4-layer regular PCB. It's less than £100 depending on what your reliability is. So there's a very, very stark contrast between kind of hobbyist pocket cubes and the sort of price that this is going to end up at. So something else we're looking at is kind of how do we achieve this result without this big rigid flex assembly? And we're looking at things like board to flex connectors, and still trying to maintain the structural aspect of this while also using board to flex connectors is kind of difficult. So we're really trying to find out how we can simplify this but keep the benefits of that really compact system. So taking some of the lessons from this and how do you fit really highly optimized PocketQube hardware into a very, very small volume. This is something else we're working on with my company, Citadel Space Systems. So it's kind of asking the question, where are PocketQubes useful and where will they be useful? And the idea is that we don't think they're only useful for amateur space, and we don't think that they're only useful in low Earth orbit. We think that amateur space is applicable beyond low Earth orbit, which has previously not really been done. And we also think PocketQubes are applicable both in general for science or for private industry, in exotic destinations like around the moon or planetary destinations. So Citadel Space Systems is really here to try to create inexpensive yet reliable nanosatellite platforms for deep space. That is obviously applicable to low Earth orbit as well when you've got really long flight times. Obviously, most CubeSats right now are around 6 months to a year kind of lifetime. We're sort of targeting 3 to 5 years and up, which is applicable both to obviously low Earth orbit and deep space. So this is kind of our flagship capability that we're working towards, is a 12 to 16 CubeSat for deep space flight. And kind of having this capability leads to being able to fly PocketQubes to very unique destinations. So this is the PocketQube that we're working on. This is called Squire. This is the 3P version of it. There'll be a 1.5P and a 3P version. And we're using the kind of the lessons learned from TFT-Cube with this flexible harnessing and rigid flex stack-up design to try to maximize the internal volume here and maximize the amount of systems that we can fit. And this is really, really useful and kind of necessary for deep space because obviously you don't have a magnetic field. So you've got to be able to deal with things like attitude control, which is all well and good with reaction wheels, but you have to have a way of detorquing them. And so being able to fit in things like attitude controlling electric thrusting, propulsion systems, that kind of thing, it's difficult to do unless you're really optimizing all of the volume inside. And so the lessons learned from TFT-Cube are being very much applied to this platform design here. This has 20 watts at Earth, which translates to about 8.5 watts at Mars, which we figure is more than enough to be able to do useful things. And the kind of the crux of this is that we're looking at up to 9 of this platform being deliverable by a 16U CubeSat. And a 16U CubeSat isn't really that expensive if it's ride sharing somewhere in comparison. I say that expensive. So really, this CubeSat delivering PocketQube concept we think is quite a unique but inexpensive way of delivering PocketQubes to destinations that they haven't been able to go to before. And so kind of in that vein, this is another concept we've briefly been looking at, and it's a bit different to where PocketQubes have gone yet. This is a 6P PocketQube that we've been looking at. This sort of larger design is mostly made possible by the fact that we've developed a slightly different standard. So if you look at what we've got here, there's a base plate on the bottom. What we've actually got with our standard is a base plate on the top as well. And that allows us to expand this and kind of maximize our internal volume and maximize the amount of space we have for both platform systems and instrumentation. So this one has about 30 watts at Earth, 12.5 at Mars. And this is kind of, both the 3P and a potential 6P are kind of instrumental for us envisaging PQs as platforms, both for science around other targets like near Earth objects or planetary targets and things like that, as opposed to just AMSAT things around low Earth orbit. So we want to see this kind of next generation of PocketQube really take off and show that these kind of really, really small satellite platforms can actually really be useful. Special mention to Applied Ion Systems, who we're collaborating with to develop electrospray propulsion. We've been working to implement these in both PocketQube form and CubeSat form. And so we'll have some more information with that over the next few months with any luck. So the last bit to round off a bit about this standard. So really what we're doing is taking the lessons learned from the Alba, Delft and Gauss standard and trying to both apply it for deep space use and fix a couple of issues with it. So the Alba standard has a single base plate mounted in rails. We have essentially the same thing, except we have an extra base plate on top. And the idea is that this eliminates the rotation that was seen in some recent PocketQube launches. So your PocketQubes will deploy A, slowly, and B, stably. So very high degree of stability and a very, very small amount of delta V from the actual deployment, which makes it very, very useful for PocketQube deployments around things like near-Earth objects, where you're doing very, very fine adjustments to get into a certain orbit around that object. So both of those kind of characteristics make this very, very useful for deep space. The deployment that we're working on, the longbow deployer, is mostly applicable for being mounted inside CubeSats or other small sats. It's not really designed for mounting on large launch platforms. So it's kind of unique in the market as it stands. And so we have an example here where this is what we call the cluster config, where it's actually kind of tighter than the Alba setup. But this is what the deployment looks like when it's a 3x3 3P PocketQube deployer, so 9 PocketQubes on one CubeSat. For small amount of PocketQubes, this gets bigger, and the idea is eventually this becomes able to supply a larger external deployment volume than the Alba one. So things like the larger solar panels that we saw, or bigger antennae, or things like that, that becomes a lot more feasible with a platform that can do this. The other key point is that this is completely back compatible with the open standard. This base plate dimension is exactly the same as Alba. So a square CubeSat can fly on an Alba pod. A unicorn or anything designed for an Alba pod can fly on this to deep space destinations. So it's very, very flexible. We're not looking to kick other people out of the market. We're not looking to make PocketQubes difficult to fly. We're very much in the business of trying to open up more destinations for people building interesting small sats. And the other key point is that we're pushing this draft online very shortly. So thank you very much. These are all my links. If you have any questions, I will have a look at the Zoom button now. Doesn't look like there are any questions. So.
Any questions for Ben as we get our next speaker lined up?
How can one join the flame? So the flame trench was, it's not, I don't want to say it's a closed group. So it's a group that we founded as people who are networking together. However, as we start to open up TFTQube as a kind of a more community-driven project, obviously most of us are already working in the industry ourselves or studying, etc. And so dedicating kind of lots of time to TFTQube is kind of difficult, and we're looking to kind of open it up. So we will make that clearer as we have a better idea of how we're going to run that. We do want to make it as open as possible. So yeah, there'll be more information about that coming up shortly. I have a question here about radiation tolerance of deep space PocketQubes. So there are kind of a few things that make this possible for us. One of the first things is that there is a greater prevalence of electronics components that are kind of COTS level pricing, but still very, very radiation hard. So the kind of best example I have of that is things like the Virago microcontrollers, which are made with normal silicon fabrication processes. So they're not inherently expensive by how they're fabricated, but they're still fully radiation tolerant. So using technologies like that can keep costs down for the amount of reliability you get. The other reason is that actually a lot of COTS hardware is more radiation tolerant than people think. Things like the Marco CubeSat flew a off-the-shelf single board computer as an instrument controller for one of the cameras. And that was operating pretty consistently during like a 7 to 8 month cruise to Mars. And I think that shows that for at least total ionizing dose, commercial electronics are reasonably well protected, or at least reasonably tolerant. And so if you do protection by design to kind of limit the impacts of single event effects, like single event latch-ups or upsets, which can be mitigated by things like your memory design, your software design, and your power systems. Actually, you can make commercial electronics reasonably radiation hard themselves. And so a combination of that plus certain hardened components can actually up the reliability of PocketQubes quite significantly.
That was great, Ben. So thanks for the talk. It was great. Stefano from TU Delft will now be speaking further on the Delphi PQ, touching on topics that Alessandra was talking on. So are you able to share your screen, Stefano?
Yes, sharing my screen now. Let's see if it all works. Do you see it?
Yeah, that all works well. Does everyone else see it? Okay.
Okay, thanks a lot and welcome here. Alessandra already presented the project, so I'm not going to go so much into the project. I'm going to show quite a lot of fancy pictures, which were basically taken in the previous months. So first, well, this is Delphi PQ. This is a 3P PocketQube, as Alessandra mentioned. And as you can see, we have a deployable antenna on the side, and you can see it in both configurations, deployed and undeployed. Well, this is how it looked last week. Now it's nicely in a box, and I'll show you instead what's inside. Well, this is actually the satellite seen from the inside. You see one of the side panels that has been removed, and you can have a look at the complete electronic system, all the electronic systems in there. We start from the top, and you can see what we call the antenna deployment board. Basically, this board is constraining the antennas to remain attached to the spacecraft, and after deployment, there will be a burn wire that will release the antennas such that they can deploy in the final configuration. If we keep going down, you can see just below the antenna deployment board, you can see our power system, which is actually hooked up to the battery. The battery board, you see it hidden inside this nice box. This is a 3D printed casing, which is mechanically holding the battery cells to give us a little bit more rigidity for vibrations. These boards are directly connected to each other, and they're also kept very, very close, such that most of our, let's say, power section of the satellite is on this side. Well, the rest of the power section of the satellite, you don't see it so much, or you can see it somewhere here at the back and around the satellite, because all the solar panels have been, all the electronics for the solar panels has been placed on the solar panels themselves. So electronics fits on the inside, and the solar cells fit on the outside. At the beginning, our idea and our wish was to have a wireless satellite, basically no wires running around. In CubeSats, this is kind of a problem in the sense that when the satellite density increases, it gets more and more difficult to fit everything. So it's a little bit difficult to see, but if you look at this small section here and here, all the connections that we have in between our battery board and the solar panels are done using spring-loaded connectors. You can see them as well a little bit in this area, where the solar panels kind of press against the battery, and this system assures mechanical contact and also electrical contact. We went through a vibration test, and we also basically qualified the system, because one of our biggest fears was rattling or small movements of the spring-loaded connectors, causing basically degradation of the PCB. But that actually didn't happen during our tests. So we're very, very happy of the functionality of this system. If we keep going down, we have this gap from which you see some parts of the power electronics. Below, you can see our, well, okay, I'll skip that. You will see these two boards, this one and this one. They are connected with wires, basically because they have to go through this metal structure here. This is what we call BOB, or the breakout board, which is basically used to join two separate stacks, because we have the top and the bottom stack. If we keep going down after the breakout board, you can see our onboard computer, and you can see here also our SD card used for storage. And if we continue all the way down. We see our communication system, which is directly mounted. This is the communication system having a dedicated board for our power amplifier and low noise amplifier that connects directly to our antenna facing board, which is all the way here at the bottom. As I said, we aimed at a satellite without wires. Well, we're almost there. We needed these to connect the breakout board, and we also ended up with an RF cable on this side of the satellite. And now we will see a little bit more about that. Well, if we look at the payloads, we have our attitude control system, which is having coils wound on a 3D printed spool. And we have 3 coils, one inside the other. What you see here is the Z-axis coil, which is the biggest, while the other 2 are inside. This is one of our payloads, and we will use it to give the possibility to students, as part of their education, to write an algorithm for attitude control. And as we are an aerospace engineering faculty, this is one of the courses students have to do in their curriculum. So what we will aim at doing once we're in orbit is have students write code to fit on the ADCS system and basically do in-flight software update, such that more groups will be allowed to test their algorithms. On top of that, we added a set of laser reflectors that you can see here in the middle. There's 4 of them, 1 per side, and they are mounted on this metal bracket. The main rationale for these laser reflectors is being able to know the position of the spacecraft with an extremely high precision. We are in the order of the centimeter from the ground. One of the rationales for going for the reflectors was that, well, a lot of people were scared that the orbit determination for PocketQubes would be much worse than for CubeSats, having basically a much bigger error. And with this, we want to prove this is not the case. So after launch, we have already had contacts with the International Laser Ranging Network, such that we can track the satellite and compare our position from laser measurements and from radar measurements. If you continue going down, we have another board here in between, just below our onboard computer, which we call secondary computer. That's almost the same system, and it's not used by default. But the goal is giving the possibility to students to write their own algorithms. Imagine, for example, analyzing the telemetry on board for some purpose. Well, that we can do on this board, which is basically listening to everything that is communicated on the satellite bus. There is no software right now, so basically it doesn't do much more than say, hey, I'm alive. But our goal is to give students the possibility to write software, and then we will upload it to the spacecraft later on. Last but not least, we have another payload. This comes from a collaboration with another Dutch group, and which aims at building a low-frequency radio telescope in space. And with this mission, we're demonstrating some of the first building blocks. What we have basically is a low noise amplifier that is actually fitted here. That's the board where the cable comes from, which is supposed to receive extremely low frequencies. And we're talking between 500 kilohertz and 30 megahertz. Of course, we don't have a big antenna for such frequencies, so we only have to rely on those small 18 centimeters long rods. But actually, we're not looking right now at astronomical sources, we're looking at Earth noise. So our goal is characterizing the Earth noise and demonstrate that our low noise amplifier works. In order to do that, we also have a readout board here that will acquire measurements. So let's go. Now, what am I going to talk today? I'm going to talk a little bit more about our integration. But before we reach the integration, there's a lot of testing that has been done. In particular, we decided to start with automated testing for several reasons. One, and I think one that proved our concept was very valid, is the fact that the university entered the lockdown in March, basically forcing everybody to work from home, including students that were working on the project. In that sense, it was impossible to have people on campus to actually test the boards. So what we built was an interface board that you can see at the top, which is connected via USB to a computer. The computer runs an application that is exposing all the satellite bus directly on a WebSocket online. This basically meant that students could simply, from their home, write a simple script that would communicate over a WebSocket and that would directly communicate with the satellite bus and all the satellite subsystems. This allowed them to do a lot of testing that they would not have been able to do otherwise. What you can see at the bottom is that we also shared most of our software on GitHub, so you can have a look at the testing software we developed. Automated testing gave us a lot of other possibilities. In particular, we have dedicated test tools which generate automatically test reports. You can see an example here at the bottom, where all the different boards have a standard set of tests that are executed. We simply need to plug the board on our system and run the test script. This can be done from home or from the computer in the lab. And basically what we get after a few minutes is a complete test of all the functions. We created it in a hierarchical way such that we can share code between all the different systems, such that we can test, for example, the standard services that every board has. And quickly, as you can see here, within a minute, we can see which functionality of the system is working or not. This was actually key for satellite development because we found out that in the last weeks, we had still a lot of work to do because of delays in the project, and testing could not have been sacrificed there. So thanks to this system, within minutes, we could see if a board was running or not. We also developed more complex tools. You can see an example here of our power system testing tool, which basically allowed us to leave the power system together with some other boards running for days and days. And what we were simply doing was collecting the health of the battery, or for example, simulating power incoming from a power supply and seeing how the microcontroller would react. This allowed us for test durations of up to 10 days right now, which allowed our software to be rather robust the day we started the final integration of the satellite. Well, one example of what I just showed you, this is a test which we did by applying power from a lamp in the lab and basically recording for a long time the behavior of the system. We had these tests, as I said, running for days, and that allowed us to build confidence on the system. By reusing most of the software on the different systems, we basically created a fairly robust architecture that we hope will prove itself in space shortly. Some other tests we performed, again, most of these things were done from home or at home, basically because most of our testing period happened during the lockdown. This is actually a test that was run at Shevket Place. So you can see an engineering model of the satellite having actual cells, which has been put in front of the lamp. And this lamp was providing power, and at the same time, we used the telemetry that was acquired to validate our thermal models, basically brute forcing the thermal properties of the system, conduction between boards, radiation, and of course convection, as in this case we had no access to a vacuum chamber, to basically optimize the models. And as you can see, we managed to fine-tune quite a lot, most of the properties, as most of the phases we can see clearly that simulation and measurements were very, very close. This allowed us to build quite a lot of confidence in the overall system, such that the testing phase in the end, in the last weeks before launch, could be much simpler. I talked about the antenna deployment board, and now you can see a close-up of this board. This system is holding the antennas. You can see the 4 antennas, 1, 2, 3, and 4, being held down. They're held in a recess on the PCB, and by holding them there, we also press a deployment switch. 4 burn wires are used on this board on the external side to retain the antennas. And we use these 4 resistors to basically burn the wire. Testing was complicated as the burn wires in the end, with this configuration, they require quite a good precision in length. This is something we couldn't really achieve ourselves by basically tying the knots ourselves. So these are commercial wires that have been bought from our partner ISIS in the Netherlands, well, located less than a kilometer away, which could provide us with these standard wires, which are fairly good in terms of repeatability, because the length of the different wires is fairly constant. And this we found out being one of the hardest part in the process. What you can see the length being fairly constant by the fact that all the springs are roughly the same length. Also meaning that the pressure or the force on each antenna and on each burn resistor is constant. Why is it important? Because this gives us very repeatable conditions for the deployment. And you can see here at the bottom a thermal picture taken during the deployment of one of the antennas, where we were monitoring the temperature of the 4 resistors. And in this case, you can see the whole resistors burning up all the way to 160 degrees. We reached this roughly in 3 seconds at deployment, just to ensure deployment is successful. But of course, we couldn't really do these tests for the whole duration of the project because the bus was not complete. So some of these tests have actually been done using dummies. You can see here this nice wheel, which has a weight of approximately 300 grams. This wheel, basically hooked up to the burn wire, gives almost the same tension on the burn resistor, and this allowed us to have very repeatable tests. We also started doing some testing on our Helmholtz gauge. This is located in our clean room in Delft, where the satellite could be experiencing magnetic field as if we are on Earth, orbiting around the Earth, sorry. This gauge is also used to kind of counteract the external magnetic fields, such that the magnetic field in the center of this table is cleaner. What we want to have is a second satellite that students will use for their development on the ground, so they can fine-tune their algorithms. At that point, we will upload the code and make sure that everything is tested in space in the exact same conditions as it was on the ground. Well, let's go to the integration. I told you quite a bit about our testing, but integration. What did we do? Well, that's the core topic of this presentation, but I really wanted to show you one thing before going on, and it's the amount of hardware that actually was involved in integration. You can see here on the left side, these are all the boards we built. Okay, not all of them were inside the satellite, because we built always 5 boards. Every system was built 5 times and in a batch. This allowed us to get a production process to be quite repeatable, and also to not be too worried in case one of the boards is malfunctioning. Some of the connectors we used, as you can see here in this picture, are quite high density with small pitch, and these caused some issues in terms of short circuits or other problems. But again, this was not very critical, as only 1 or 2 boards were affected. But because of the final moments in the integration, we could basically decide not to test one of the boards and just leave it aside and focus on the 2 or 3 that were perfectly functional. So here you see all the subsystems with their flight spares being ready to be brought into the clean room. In the center, you see a picture of our clean room when we started integration, where you also start to see all the dummy panels, all the actual flight panels, spacers that were used, and all other components, thread lock. So there's quite a lot of hardware that in the end ended up in the satellite. You can see here on the top right corner, basically the 2 metal plates that build up our structure. And you can see below a picture from our partner Airbus in the Netherlands, which glued the solar cells on the panels. And actually, these are regular solar panels that they built, in this case, the Orion solar panels. So next, well, integration was fairly traditional in the sense that it's very much deriving from the CubeSat experience that we had. So the satellite internally is a stack of boards. And as you can see here and here, all the different boards have been stacked using stack-through connectors and spacers. Well, the solution is used by almost everybody, and we had calibrated spacers for the different combinations of boards. This is reasonably easy as a solution, but has the downside that you really need to have a lot of different spacers, as you can see in these boxes. So we basically have the complete series of all the possible heights in steps of 1 millimeter, such that we could fine-tune the integration. You can see here as well, in this corner, the satellite being built a bit more, with more boards popping up onto the stack. We are also ready at this stage to insert the laser reflector holder that you can see here, that will be fitted onto the stack, and where these wire coming from the breakout board will fit into the hole in the middle. Now, further in the integration process, you can see us assembling the attitude control system onto the stack. Actually, this was a first try, because in the end, at the last moment, we decided to swap it, because in the end, one of the downsides of these spacers is that you might build up a bit of tolerance after stacking several spacers on top of each other. Electrically, tolerances are not really a big issue, because the connector has a quite long, let's say, stroke, or such that it doesn't really need to be pushed all the way to the end. But of course, this metal bracket in the middle holding the laser reflectors has to be correctly aligned with the solar panels on the side. So the buildup of tolerances is sometimes a downside of this integration system. Well, in the end, it fitted. You can see a tired colleague. You can see Shefket now after about 4 hours of integration. And yeah, it was a long day. And this was the day before we did the vibration test. It was quite long, because basically the satellite had to be integrated for doing most of the testing. But then, of course, you don't want to do all these testings in clean room, because it's going to cost you more time, which basically meant we had to dismantle all the spacecraft, clean all the boards, and exactly what you've seen in a picture before, where all the boards were on the table, clean everything, bring in clean room, and then integrate. So, and then after that, we went for flight preparation, gluing all the different screws, because one day later we had the vibration test. Well, we mentioned tests. These are the tests that we performed in the last couple of days of the satellite integration, which we started with a vibration test, thanks to a company in the Netherlands, to Thales. We were allowed to go during the COVID period, which was very complex to organize. And we managed to have a complete 3-axis vibration test, after which we had, again, electrical testing. Then we went into bakeout to be sure that all our systems were not still containing volatiles that could damage other spacecraft in the launch. Basic testing was also done after the bakeout. And to conclude, we also had the opportunity to test our radio directly with the ground station. The ground station is not located directly on our building, but it's located in another building in our campus, which is about 2 kilometers away. But in the end, thanks to the directivity of the antennas on the ground station and the power of our radio, we basically were able to receive from our building. And another nice test, you might not see much about it, but of course we wanted to see if our laser reflectors were okay. So we had to turn off the lights and check. And as you can see here, the reflection of the laser reflectors before we shipped the spacecraft. One important thing I want to mention, if somebody else will go into such a project, you need to keep an eye on your quality approach. This is key, because as you've seen in the previous slides, we had a lot of boards. We integrated 8 or 9 different boards, of which 5 of them was built every time. So we're talking about roughly 50 different boards flying around in the lab, all of them being prepared for flight. Some of them having issues, actually, as you can see at the bottom. One of the boards had a very last moment issue that we never really noticed during the previous steps of integration, basically because one of the stack of connectors had a certain resistance, And this, once everything was integrated on the flight model, was actually limiting the current reaching the burn resistors on the flight model, also limiting the temperature. What was actually realized was the fact that one of the layers of the PCB was actually not properly designed, or basically the width of traces was not enough. For 3 resistors, this was not a problem, but actually for one of them, this was a problem. So in the end, of course, at the last moment, we had to arrange a solution adding extra wires. What is really important if you aim at building more projects is to keep an eye on all these issues. That's why we relied on mostly software solutions. Like you can see, you can clearly recognize GitHub. Well, basically, most of our production issues have been tracked on GitHub. We also tracked all the development stages, basically creating issues or features to be added in our GitHub repositories. And in the end, we also looked at more automation, basically ways to keep track of all the issues across multiple repositories. As you can see here, all the issues have been tracked in dedicated projects, such that we could see if something was ready or not. Basically, checking what is still left and what has already been completed. This was actually quite a lot of work, and I really think you should consider it if you're going for such a project. Well, I already started to spoil a little bit the lessons learned for the project, but definitely building spare boards is something that really helped us a lot. In case one board had malfunctioning, we didn't really have to spend time debugging it. We basically had the opportunity to simply switch. We have now a stash of boards which is, well, still needs to be checked, and we will use them for our engineering model on the ground. But we didn't really have to waste time in case of problems, and this cut our integration time a lot. Tracking issues is fundamental. Don't forget about this, because sometimes issues are repeating on different systems, and if you don't have a proper tracking, that's going to cost you a lot of extra time. So GitHub in that sense helped us a lot. We gained quite a lot of practical experience with 3D printed parts. All our 3D printed systems were done using Ultem 9085, which is a material that has good mechanical properties, and it's also very robust when it comes to vacuum. So also outgassing level during bakeout were very minimal. But 3D printed parts are not always ready for, let's say, prime time in terms of production. You see a lot of times parts of the material which are not properly cleaned up, or parts which are protruding. So that will cost also quite some extra time to prepare the components to be integrated on a spacecraft. Of course, I'm going to say it 3 times, but I probably should have said it 25 times. Review and testing is key. You really need to keep an eye on that, because again, you'll find problems for sure, and catching them as early as possible will cost you lower time, much less time. In our case, a lot of the issues have been tracked early in the project phases, so we could accommodate for new revisions of the systems. But actually some issues, as you've seen in the previous slides, were caught all the way at the end. And that's actually, it's really a pity, and it costed us a lot of time to fix it. So again, I'm going to stress again, review and testing is fundamental. Quality control was also very key to us. What we saw is that after 4 revisions of most boards, we were basically able in every production run to get all the 5 boards we were producing to be flight worthy, all of them. This gave us a lot of possibilities to try new things. Well, we want to try a new solution for a problem that we encountered. We're not going to do it on the flight model. We have plenty of spare parts to do. So this was something that helped us, again, keep the development time quick. Last but not least, make sure students are having fun. Well, we have used a lot of students. They have been involved in the project. Unfortunately, not all the way to the end, because due to the COVID situation, the campus was closed for students and only staff members could be present in the lab. Nevertheless, you can see the satellite here in one of the last pictures we took. Basically, after this picture, the only thing we have done was flight preparation, which basically meant refurbishing the burn wires that you can see would have been fitted at the bottom, and put the satellite in a box. Well, here we are. This is the end for now, we hope, where in the end, the satellite is ready for shipment, and it's actually now all the way in UK, ready for integration tomorrow. Now, this is the team that finished the spacecraft. We reached the end of this presentation, and you can see on the right side, Delphi PQ, inside his nice little box, hopefully getting closer to his siblings in space, Delphi C3 and Delphi Next. So with this, I am done with this presentation. And yeah, if you have questions, please go ahead. I see 3 questions. Wait, okay, here we are.
Sorry, we've kind of run out of time. So we're moving on to the Satellite project by Ariel University in Israel, and presenting is Dr. Boaz Ben Moshi.
Hi all, can you hear me? Can you hear me?
Yeah, we can hear you good.
Perfect. So thanks for the opportunity of giving a talk in those weird times. My name is Boaz, and this is a joint work with a group of students of mine. And I will state how much they did. I'm the presenter here, but really my part in that is mostly the vision and helping with, bringing coffee and pizza in COVID-19 time. Anyway, I'm going to give a presentation about a concept of Wi-Fi from space. But before that, I'm going to give a little bit on the satellite project. Sadly, not all the what we planned to have is actually in our current satellite, which is in Alba in integration. But the vision, hopefully, the entire vision I'm going to present here, going to be in the next satellite. So let's start. So basically, the notion of SATLA is an educational program of how to make students involved in new space, how to make, instead of a faculty project or an industry or university project, how to make a blend of everything, mostly interdisciplinary. Most of us are not engineer of any sort, and we cannot solder anything. The main goal is to have a laser communication link for extremely high into a gigabit per second laser link to towards Pico satellite. And as a partial steps, we think of doing some sort of Wi-Fi. This is going to be the main topic of this talk. And also the concept of multi-ground station as a concept where you not necessarily have your own ground station, but you use thousands or hundreds of other people, other organization ground station. In preparation or integration, actually SATLA-1 is a 1U satellite, which is already in the ISS, ready to be launched, hopefully in the coming 3 or 4 weeks, sometimes in early November. I will elaborate more on it. SATLA-2 is our current in integration in Alba facility 2P satellite, and then in our thoughts and in our COVID-19 engineering, our SATLA-3, which is more of a remote sensing serious satellite, and SATLA-4, which is the even numbers are more of a U standard, more of a serious satellites, and the odd numbers, and the even numbers are serious research stuff, meaning we try a lot, not necessarily we'll get it all in the first time. So SATLA-4 should be a Wi-Fi video, real-time video transmitter and an IoT service from space. And what you can see here is the SATLA-4 or SATLA-2, sorry, laser beam from about 10 kilometers from the university. And this is the little satellite here on the image. Right, so the goal is to have a laser communication, laser link from space. Obviously that requires an extreme accuracy from the attitude control determination in the system, and something which should be significantly better than a sub-milliradian accuracy, and have the ability to do dynamic tracking of not star tracker as such, but mostly a ground tracking towards sub-milliradian tracking, which is a quite complicated issue on a large satellite, but on a tiny satellite is a big deal. And the ground station point of view, we have a kind of a telescope which points to the satellite, and hopefully using fast avalanche photodiode can transmit, can interpret the pulse of lasers towards data as if it was a fiber. This is a little bit few words about SATLA-1, which is currently in the ISS. Hopefully it has Raspberry Pi as their kind of, if you would, the main payload boards, 2 of them for redundancy. We're not sure it's going to work. Each has their own 8 megapixel cameras and OpenCV and Python. It has an array of LED. You can see that here. Hopefully with an amateur telescope, you should be able to detect that and have some interesting experiments with GPS, IMU, and time of flight RF ranging from that. And we have some sort of option to upload Python scripts to that satellite. So some of the interesting experiments, we're not fully developed them because we said, that requires good programming, and hopefully, and there's no reason to do that before we have that satellite working. SATLA-2 is a 2P project currently in the ALBA facilities. It has 3 reaction wheels, as you can see that here. It's actually brushless motors coming from high-grade drones, and it should be able to perform 3 ASICs accurate aiming towards kind of LED or a laser beacon from ground. It was built, as others mentioned, in a COVID-19 engineering, a lot of 3D printing, a lot of improvising, and we're not fully sure all the things will work. But we do count on LoRa, mostly UHF, and then LoRa on the S-band, and I will elaborate a little bit more afterwards. In a nutshell, we're not an expert. We know very little on space, and we're not a very engineering group. We're more of a research group that loves toys. We're grown-ups that love to play with toys and gadgets. And for years, we've been playing with high altitude balloons. Most of our practical experiments are to take our electronics and put it into a near space condition with the balloon, and hopefully see if it works. This is the way we practice stuff. It's more fun. Sometimes it's depressing because not always it's been working, but a few times we got it right. And using that kind of a notion, we've been able to hack Wi-Fi towards from 100 meters average distance towards 30 kilometers, and that helped us to bring those kind of little drones. This is like a kite that has tiny little motor and autonomous flight back towards the campus, and 1 out of 3 or 4, it actually goes all the way back. So this is our testing facility. This is actually the drone bumping into the university fence, but we got all the way back. This is me doing low-tech, high-altitude balloon payload. This is while the COVID. This is on April, where I'm teaching other universities and other high schools of how to do a payload with a Wi-Fi transmitter, a long-range Wi-Fi transmitter, a GPS, flight controller, which is the black part, it's a PICSOC on the left, and no soldering. So just by duct tape and USB connectors. And the electronics cost about like $200. And a lot of universities and other schools are doing that. And this is actually an image of, eventually I got it to work. This is actually an image taken from about, let's stop that and let's think. So this image was taken about 60 kilometers, 60, from the university, 10 kilometers up. And it gives us, this is using a standard Wi-Fi. So how do you, so the big question, the big topic I want to share here is how you take standard hardware of Wi-Fi and you benefit it, you push it from say a few hundred meters towards 100 kilometers, and in a few slides 1,000 kilometers. So the idea is that you don't need to do any electronics yourself. If you take commercial drones, two of them which are very known for the long range, or there are Mavic 2 Air and the Xiaomi Fimi, they can do 10 kilometers full HD transmitter on a standard antenna. If you use FCC-wise, if you use directional antenna, like you can see here on the image, you can go to 100 kilometers. It won't necessarily be, flawless video flow, but in most cases you would get a proper video. But you do need some sort of hacking. A very good software, I cannot emphasize enough how helpful they are the easy Wi-Fi broadcast and all their forks on the internet. I will point to a certain fork of them, which is extremely helpful to hack the Wi-Fi. Basically, it detaches the need from having your client being associated with the router. The client basically transmit, and any associated router, not as unassociated router, may be able to transceive that and get the information. So this is a Raspberry Pi 3 connected to Wi-Fi cards, and basically with forward error correction, being able to perform high altitude balloon from say 100 kilometers. Some sort of practice on the right-hand side versus theory. So if you take theory, 30 dBm Wi-Fi FCC transmitter with 8 dB gain, you do the math and you get 160 dB budget link. That should be able for allow you to have some sort of low resolution, I would say 1 to 2 megabit per second from space. If you take practice, and this is the our approach, you take whatever you can find on your shop as a Wi-Fi card, and you plug it in. You have a standard TX antenna, and then and a standard TX a receiver antenna. And the sensitivity is not as good, but in that practice, we've been able to have a relatively good video link for 270p, whatever. It's like not full HD, but good enough for 30 kilometers. And you get an extra 36 dB to spare. You do the math, you divide it by 6, and then you do to the power of 2, and this is shows the applicability of doing it from low Earth video. And this is basically the numbers here. You can see the GPS, the signal strength, the height, and keep in mind that in those high altitude balloons, basically you are very close to the horizon. Although you are maybe 10, 20 kilometers up, you are more than 100 kilometers away, and your 2.4 gigahertz Wi-Fi transmitter is fighting the thick atmosphere it needs to cross. And in the path of a satellite, that things are not as hard. So this is how you push it towards low Earth orbit. So basically, the here link, we were not using it on high altitude balloons because they're quite expensive, but they can do 20 kilometers easy on FCC on Wi-Fi link. You have 2 HDMI, so you can do both selfie and the other camera transmitting it together. Bidirectional antenna, you can get a factor of 10. Okay, so this brings you to around 200 kilometers. To push it all the way, you need a good forward error correction, and I cannot emphasize enough how open HD is helping with that. Their community is amazing. They're doing amazing Raspberry Pi based piece of software that helps you do all the forward error correction, all the two-way channel of controlling your drone or your whatever your satellite from the ground station. And yeah, they're doing an amazing job. Recently, we found a work we were not aware of that in 2016, just lately, I think it was a year back, the world record of having a continuous, perfectly Wi-Fi video was break, and they got over 300 kilometers, allowing minus 70 dB. So obviously they can do 10 times that. And we were able to do the same experiment with cheap, significantly cheaper and more affordable communication, and using FCC standards, and having about 100 miles or 160 kilometers of a video link using standard hardware. You can see here the antenna. Right. So pushing it towards a little bit more than 500, because obviously you think of a 500 kilometer, but most of the passes are more in the neighborhood of 1,000. This is hard. So the last 6 dB are kind of hard. A rich organization solution will be having a good ground station, a big ground station antenna. Those are expensive. And having a very good SAT antenna. Those two solutions are complicated because yeah, it requires a lot of engineering. The amateur solutions, or the good programmer solution, would have putting a lot of emphasis on good forward error correction and playing with the parameters of the Wi-Fi, and do a dual solution of both 2.4 and 5, because the pros and the cons are of both of them are kind of weather dependent, so you might want to have them together. We found a work just recently. I actually, frankly, I haven't read it through. We know that in 5 years back, the use of Wi-Fi were shown almost 400 kilometers video link. And the way they did it is they basically took commercial off-the-shelf devices, and it worked for them. So I would say that a better Wi-Fi, newer Wi-Fi devices with some better ground station could help mimic their solution. And here's in a nutshell, this is the only important slide you need to remember. So nothing about us, or very little about us. First of all, Amazon is currently allowing AWS ground station service. We are with, say, initial cooperation with them to test 2.4 LoRa, 2.4 gigahertz LoRa with them on their amazing, huge, extremely expensive ground station. They have a few ground stations spreading around the world. You can pay as you go with them. And on an S-band, it shouldn't be more very expensive. So if you have your packets and you want to pay for having a proper images, and you don't have the time or the efforts to have a serious ground station on your university, this might be a very good solution. We are working strongly with the amateur, the radio ham amateur, to have a $100 ground station. This is LoRa based, and this should be able to help us to do some sort of LoRaWAN gathering of information. Another concept we play with is to have a telescope ground station, a laser ground station. This is a complicated topic. It raised a lot of interesting, complicated problems. So I will bypass that and just say that if you have a telescope, if you have a robotic telescope, and you can record the video with the and record the data with a with the avalanche photodiode, and you just can you maybe get a few dollars from someone just said, can you follow my my satellite? I just want to blink a few seconds of laser. That might be a very good cooperative way of having your satellite LED or laser transmitting through unlicensed band. And obviously Wi-Fi, the lowest point, Wi-Fi is the most suitable device for multi-ground station. So trying to summarize things. So obviously one big question that I have a master's student of mine keep asking whether should we go for the lower frequency 2.4 or the 5. Obviously 2.4 has a lower space loss, but it's an easier to hack and amplify. And there's a way more experiment than that, but the 5 frequency seems to be more suitable. A, you can have better antennas, both on the ground and on the space. B, you can have you have higher bandwidth. And most long-range drones use 5, and there are serious people there. And why not use both? If you get a good alpha cards, you can have them both. So it's not actually a question. We've been actually took us quite a while to understand that you don't really need to do the comparisons, and one most advanced and modern cards have them both. Yeah. So so last slide. We're currently in our ground station. Even in COVID times, we plan to do some sort of ground experiments towards 10 and 30 kilometers for ground experience for Wi-Fi, for long-range Wi-Fi. And this could be an open link for others that want to work. In early November or late October, it's not yet given the time, we plan to do a high-altitude balloon experiments to try and have a solid 200-kilometer video link on Wi-Fi, and on standard Wi-Fi, meaning standard COTS, not amplified Wi-Fi. And yeah, and currently we're working on the notion of 3P SAT with hopefully next year will be launched from Alba facility as well. And there's a lot of issues to do, the antenna, the attitude control, the power to deal with the Wi-Fi, and also the notion of multi Wi-Fi like or ISM like ground stations to cooperate with others seems to for us to be like a very good common ground for cooperation. So we are open for cooperation. We're not a business of any type. Let me just summarize that to build yeah, it takes a small tribe to build a PicoSat, mostly in COVID-19 times. I want to especially give my deeply thanks to Amit and Ronnie and Revital and Aaron, Michael and Liran, that together they're all students. They all drank a lot of Corona beer in those crazy times, and combined they've been able to build this summer two satellites, and it's an amazing job. Thank you very much. I'll be happy to take a question if there are. So should I take questions? Okay, so
if anyone has any questions for Boaz, feel free to ask, and we'll have Constantine up, our RF engineer from Alba Orbital, up next, presenting on the Unicorn 2 platform.
I have a question. Can you?
2 seconds.
Hi, my name is Constantine. I'm the RF engineer at Alba Orbital, and I just wanted to ask you about the ground station you were mentioning. When you say $100 ground station, what exactly do you mean there?
Okay. So
Yeah.
So basically, it's a very simple. Assuming our satellite works in LoRa, and either LoRa 2.4 or LoRa UHF. For in Israel, we work in the 433 megahertz, but it doesn't really matter. So you get a card. It's about $20, even with shipping. You might need a proper antenna, either Yagi for the UHF or a dish antenna for the Wi-Fi. And I'm still assuming you have some sort of a computer, but if not, you would need a Raspberry Pi. Basically, that's it. We are gonna publish, hopefully after one or 2 weeks, if our satellite works, we're gonna publish how to communicate with it. It's a little bit sensitive because obviously if someone we have one channel. So if someone know our frequency, though, do some sort of just transmitting could be an easy thing. So we first want to get our few packets, but afterwards we're gonna publish the entire sketch and the entire binary, if you would, and how you can communicate to do eco, to get a lot of data, and even very low image like 10 kilobytes images through either 2.4 or UHF.
Okay, so it's going to be something that is also sort of mobile ground station as well, I assume?
Yes. It's like, it used to be like the old TV antennas, you know, those Yagi antennas?
Yes.
And I use the one that I have on my the roof of the building in my university. It's just been there forever, and we just plug it in, change the connector, and we use it. It's working. Yeah, it's mostly you need to be in a not very interfered environment, RF interfered environment. But other than that, we think it's going to be easy. In our next satellite, we think that Wi-Fi going to be the next step up, and a proper alpha card will cost you about $50. Other than that, it's another $50 antenna, and you're good to go.
Okay. Thank you very much.
Okay, so we're just going to load up Konstantin's talk up in the moment. So we're going to be sharing screen now. So can everyone hear? Can everyone see the screen? Yes? Hello?
Yes, we can see it.
Okay, that's good. Thank you for the confirmation. All right, so now Konstantin will present.
Right, so I hope everybody can hear me okay, see me. That doesn't really matter, let's be honest, as long as you see the presentation. So good afternoon, everyone. My name is Konstantin. I am a RF engineer in Alba Orbital, and I am going to give a brief overview of our technology. So the satellites we've been fabricating here at Alba. What do they do? I'll talk a little bit about their specs and give some mission ideas. So, the overview, I'm just going to briefly introduce Alba Orbital for those who are not familiar or very familiar with the company, talk a bit about our goal and why we scale down and we fly, then go into our technical overview. Excuse me. I'm going to talk I'm going to talk a little bit about the first satellite, Unicorn 1, and then go to Unicorn 2, and mention a little bit what we can do with our guidance system and what our payload capabilities are, and then also present to you, the PocketQube orbital deployer, the Alba pod as we call it, and mention a little bit briefly what our ground station is composed of. Finally, I'll finish with some mission ideas and some potential collaborations that can be done with Alba Orbital for these satellites. So pretty much our mission statement hasn't changed since last year. This slide is, I admit, from last year's workshop, because the mission statement has not changed. We want to advance the PocketQube because we want to grow the community and we want to make PocketQubes matter or great again. So why scale down? I think that is pretty much obvious, so I'm not going to spend too much time on this. So you have satellites that go to up to 2-3 tons. Excuse me, we are below the kilogram, and being more compact, so having a smaller miniature satellite is less expensive to fly. There's less junk in space, and therefore, and also we can make bigger satellite constellations. So Alba Orbital has gone down this path of the miniature satellites of the PocketQubes, along with all the people here in the community. So who are we? We are a small company in Glasgow with 12 full-time staff, and we're growing. We are working from parts to full platforms, and we have already flown 2 Alba Orbital satellites, in December 2019 for an inter-satellite link test, plus our customer's satellite, because we're not only flying our own satellite, but also other people's. So 6 in total in orbit, and we'll be flying again at the end of this year 2 Alba Orbital satellites, a Unicorn 1 and a Unicorn 2, plus again the customer satellite, both recurring and new customers. So that being said, I'm now going to give you a technical overview of what our satellites are. So what you're seeing here is Unicorn 1, or rather a CAD of it. This is the first version of the satellite that is going to fly at the end of the year. We flew last year our improved version, and we couldn't fly Unicorn 1, so we still need to fly this one. So we're flying it at the end of this year. This is a 2P PocketQube, 50 by 50 by approximately 13 centimeters, 5 by 5 by approximately 13 centimeters. It has 270 approximately grams. It has a mass of 269 grams approximately, and you have more than 100 grams available for payload. We have a 1 watt on orbit average power, and this satellite also has a passive attitude stabilization. It is compatible obviously with the PQ60 standard, and it is the basis of what we now call Unicorn 2. So from Unicorn 1 to Unicorn 2, the size has changed. We've moved from a 2P to a 3P. And excuse me, last year, as I said, we flew 2 of these satellites, 2 unicorns, and this year we'll be flying another 2 with some improvements made between the 2 versions of the Unicorn 2. So what I'm going to present next is pretty much the improvements. I'm going to show a technical overview of the improvements that have been made on the Unicorn 2 satellite from Unicorn 1 to Unicorn 2. So as I said, Unicorn 1 is a 2P satellite. Unicorn 2 is a 3P satellite. So you can see here on the left and on the right, the 2 versions. On the left, you have what we call Unicorn 2.0, which is the 3P PocketQube that flew last year in December 2019. And on the right is 2.1, which will fly at the end of this year. Now, before going into the differences of the 2 unicorns, I'm going to talk about the similarities first. So in both cases, we have kept an active attitude stabilization. So we have an active ADCS. We have switchable lines from Unicorn 1 and Unicorn 2.0 and Unicorn 2.1. We've kept this, as well as the options for available protocols. We generate a lot more power, up to 10 watts on orbit and 19 watt peak. 19 watts, not something you wanna generate right now. So the platform mass has increased a bit. We have a bit more, again, than 100 grams of available payload. The main difference, between Unicorn 2 and Unicorn 2.1, the form factor remains the same, both for the wings, the way they deploy, the body, and what is inside the satellite. We still have our guidance system, our sun sensors, our patch antennas, and our monopoles. They deploy exactly the same way. The fundamental difference is what I'm going to show here. So basically what you see here is a cut of the insides of the satellite. In this case, you're seeing the 2.0 version, which is the satellite that has an aluminum body. So the fundamental difference and major improvement between the two satellites is the body. So as you can see in the pictures here, on the left is Unicorn 2.0 again, which has an aluminum body, and on the right is the Unicorn 2.1, the one that is flying at the end of this year, which has a different kind of body. So that is the main difference, major fundamental difference that allowed us to improve this satellite. Why this? Because in the first case, on the left, we have an aluminum body. On the right, we have a body made out of wind form, which is a carbon fiber material mixed metal. I don't have the exact composition for that, but it's a more lightweight material that allowed us to improve not only our payload bay volume, but also our harnessing techniques, as well as our payload volume. It's also a material that is very thermally inert and therefore can be exposed. Takes a lot of time to have its temperature changed, which is good in our case because it provides by itself some sort of first thermal control. So I am going to mention here that, so basically I'm going to talk a bit about our guidance system and the payload capability. So on the top left, you see basically a schematic of the new body of Unicorn 2.1, the one flying at the end of the year. The payload bay is where basically you see the optical payload standing in, and you can see that if you can replace basically this optical payload with some payload boards that we have designed that you can see there. The numbers are not very clear there, but basically, like I said, this new material, we have re-optimized the chassis, so the body of the satellite, and we have variable size payloads that can go there. You can actually stack up to 4 or even 5 boards of the ones, the ones I have here and the ones you can see in the presentation. These boards can go from 95 to 102 millimeters of length by 46, which is the other side of the chassis. They are easily removable, way more easily removable than the first version of Unicorn 2, so version 2.0, and that makes it also easier to test. So that being said, I also want to talk a bit about our guidance system. Our guidance system hasn't changed drastically since last year. We still have a system that it has 2-axis sun sensors and has 5 degrees of pointing accuracy. It has its reaction wheels and its magnetworkers. And I have to say here that among all the subsystems, the guidance system is the one that requires the most power. So because a lot of it is made from brass, it can heat up very easily. So wind form being a material that is thermally inert is actually quite useful because we can actually use the wind form as some sort of heat vent. So having talked about the payload and the guidance system of the latest version of our satellite, and we've actually flown last year 2 satellites for an intersatellite mission, and this year we're flying another one, Unicorn 2A and Unicorn 1, the Unicorn 2 for an Earth observation mission. I would just like to finish this by giving 2 things. First of all, talking a bit about our deployer. So the way we deploy the satellites in space, some of you already know this, is with our AlphaPod, the PocketQube orbital deployer. So this pod can take up to 6 1Ps or any combination of 2 or 3Ps that adds up to 6 1Ps. It has a base that is made of aluminum, and the shell, its casing, is of the same material as the satellite. It's the wingform shell. So this pod, which also we used last year to fly, is actually quite lightweight, and it has been tested to meet NASA standards for random vibration. So this year we'll be flying so our 2 satellites and our customer satellites in 2 of these pods, and we'll be flying a LEO mission at 520 or 525 kilometers. It's 505. We will be using the UHF and S-band channels to do respectively telemetry and downlink our image, because we're flying an optical payload to be able to take images of the Earth. So we've also made a mobile ground station that has a UHF and an S-band channel. The UHF channel is used for uplink and downlink, mostly for telemetry and tracking and commands. And the S-band is a downlink channel only that will be used to downlink the images we've taken. And we will be having our mobile station moving around, not too much, hopefully, not too much. So for this to work, we have equipped our ground station for the UHF link with a Yagi antenna that is around 14-15 dpi, circularly polarized. And our satellite at the moment has a monopole of -1 dpi. At UHF 401, 402 megahertz, that is quite a compact antenna. So the gain you can get from a compact antenna FR4 substrates is not always the best. So this can be improved, but for now we have enough margin in our link to be able to accept -1 dpi of gain for the UHF antenna on the satellite. For the S-band link, our satellite uses, we've made a circularly polarized patch with 5 dBs of gain, PIC, excuse me, and in this case, the patch has a half power bin limit of 60 degrees. With that being said, we have a product that we ourselves have used for clients' intersatellite link mission, and this year we'll be flying our own mission to test the satellite's Earth observation capabilities. So already we have a relatively low-cost technology for commercial applications. As soon as you start putting in constellations, you can carry even more commercial applications, such as Earth observation, which is something I think people want as soon as they have like agricultural or maritime economies, or more. Actually, I'm taking 2 things that concern me, because I'm Greek, so I know these 2 things are of interest. And then you have things like RF sensing missions, which is something our clients do. And because the PocketQubes as well as the CubeSats, let's be honest, are originally a tool that was developed for education, we are also very interested in R&D collaborations, for example, trying to integrate propulsion system mini propulsion systems or deployable lenses, and we are actually working actively on trying to integrate some transparent antennas, flat transparent antennas on our solar panels, but for higher bands such as X or even X band. I'm not going to say K band, I would like to, but I'm not. So the PocketQube platform is a platform that is a low-cost technology that can be used for multiple missions and has potential for improvement through R&D collaborations even more. And this is something we are actively seeking both new missions and new people to do these missions with, as well as any collaborations that will improve the performance of this platform through people's ideas. That's it for my presentation. Thank you very much. If you have any questions, please let me know. No questions? Right. Right. So I am reading two questions. How did you recover your payload after hub launches? And does ALBAC currently have or anticipate in the near future any opportunities for mechanical system engineers in the class experience on and space system projects? So one question is technical question and the other is a recruitment question. Is that it? So the first question from Saj, how did you recover your payload after hub launches? What is, I misunderstand the word hub here, or the initials hub. It's related to the previous presentation. I'm sorry, my apologies, Saj. And does ALBAC currently have any opportunities for mechanical system engineers in the Glasgow area? I would like to say yes, but we are COVID, what's called blocked, and I would really love to add someone else, another mechanical engineer, but at the moment we're on standby for that. I would be most definitely interested to see if we can integrate some form of propulsion system to this satellite. That is, I think, a challenge, but I think it would be an excellent R&D collaboration. Thank you, Alejandro. Any other questions? I'm not seeing anything here. But regardless, if we will be, sharing all these presentations. So if you have more questions about, more specific questions about the Unicorn 2 satellite or the pod or the ground station, feel free to email Gaius and he'll get back. He'll tell me and we can get back to you. Thank you very much. Oops. And now I'll be switching, correct?
Okay, thanks, Constantine. So that's us now moving into lunch, and then we'll come back with Vicente from FOSSASAT at 2. You can check out the virtual exhibits, talk to some of the presenters and such, some of our exhibitees over at the PocketQube Workshop website, www.pocketcubeworkshop.com, and we'll see you at 2. Hello everyone, that's us back from the break. Here we have Vicente Gonzalez from FOSSASAT. He's our CTO and co-founder, and he'll be able to run through his presentation with you all. Are you able to screen share, Vicente?
Yep, sure. Can you hear me?
Yeah, we can hear you fine.
Okay, thank you. Can you see my screen?
Yes, it's looking good.
Okay. So thank you, Caio. First of all, thank you, Caio, for taking with this workshop forward despite the current situation of the pandemic. Let me introduce briefly myself. My name is Vicente Gonzalez. As you mentioned, I'm currently the CTO at FOSSASAT. It's a really big pleasure to be here with you, sharing our latest updates regarding FOSSA Constellation and FOSSASAT platform. So I would begin with a brief introduction, just in case we have any attendee that is non-related with space business or with new space business. Then we discuss a bit about the differences between CubeSat and PocketQubes. Then we will have a look at FOSSASAT-2 Evolve platform, and then we will design a constellation using this kind of PocketQubes. So let's begin with a brief definition of what implies old space and new space. Old space is mainly characterized by high cost. There are expensive long-term missions, usually supported by space agencies, that consume a lot of human resources. Normally the teams are compounded by hundreds of people. They usually take a long development time, and the operation can last for years. For example, Gaia, which is a mission with more than 6 years old. And even though the state-of-the-art technology that is usually related to old space, once launched, could be obsolete, like, for example, a satellite Ingenio. And on the other hand, we have new space, which, as far as I understand, is mainly based on private initiatives, developing smaller spacecraft based on COTS components and standardization and miniaturization of the technologies, leading to fast development time and fast constellation deployment. Just as I don't know if any of you has ever made the estimation, but in this side of the picture we can see the NBSAT, and here we can see several CubeSats and even a PocketQube, and almost 1.4 million of 1P PocketQubes would fit in the volume occupied by the NBSAT in launch configuration. So basically, new space can be understood as the solution of the so expensive barriers to entrance to the space business. We will focus in this presentation on this part of the diagram. On the top of the image, we can see the classification of the spacecraft regarding the mass, and here we can see the classification regarding the form factor. You know that we can see here CubeSats and PocketQubes. We will focus on Pico satellites, which are satellites with a spacecraft mass below 1 kilogram, and we will discuss about 0.25 U and PocketQubes. So let's start with a brief of history of CubeSats and PocketQubes. In 1999, the first CubeSat standard was created, developed by Professor Puig and Professor Twix. 4 years later, in 2003, the first CubeSat was launched, and 10 years later, the commercial CubeSat launches overtook academic and scientific launches, meaning that several companies are making business out of this kind of satellites. Later this year, in November 2013, the first PocketQubes were launched, when CubeScout, Bigger One, etc. Then in May 2018, the first CubeSats that left Earth orbit were launched. If I don't remember badly, there are the Marco CubeSats within an interplanetary program of NASA. Then in that year, later in June, the first PocketQube standard was created by Alba Orbital, GAUSS, and people from the Technical University of Delft. And then 1 year ago, in December of 2019, the second successful launch of PocketQubes was accomplished. FOSSASAT-1 was launched, as Julian mentioned during his presentation earlier today. And now we have, but by the end of 2020, the PICOBUS mission within the maiden flight of Farfly Aerospace will include 2 PocketQubes developed by FOSSA, FOSSASAT-1B, which is this PocketQube, and FOSSASAT-2, which is this PocketQube. And as Julian mentioned, in April 2021, we hope to successfully launch the first PocketQubes, FOSSASAT-2E, that would become part of our own constellation. Now let's move on to a brief comparative between CubeSats and PocketQubes. On this side of the screen, you can see how the different parameters are related. Regarding the volume, this relation is not completely true, because since in CubeSats, the volume is usually constrained by the deployer. In the case of PocketQubes, we have some margin, and that leads that if we have a CubeSat with a backplane and with deployable solar panels, at the end, the relation between the number of PocketQubes that could fit in the volume of one CubeSat is, instead of 8, it downs to 4 or 5 PocketQubes. Now we can see in this part of the image, we can see a small comparative between some of the parameters in which PocketQubes are kind of better and other CubeSats are stronger. On the one hand, CubeSat have more flight heritage. There is more codes availability for CubeSat. They usually have higher capabilities than PocketQubes. But on the other hand, usually to develop a CubeSat and even launch it is usually much more expensive than in a PocketQube. On the other hand, we have PocketQubes that reduce the cost and time of developing and launching the satellites, although the reduced volume and the reduced power budget leads to limitations regarding the applications that are usually limited to IoT connectivity services, small Earth observation platforms, data relay, etc. We will focus, as you can see, this is an overview of the type of satellites launched. As you can see, the 3U CubeSats represents the majority of the satellites launched and expected to launch. This is due to the constellation of Planet and Spire, which are based on this form factor. But we will focus on the 0.25U CubeSat and the PocketQube. As you can see, the numbers are quite similar, with 61 CubeSats expected to launch or already launched up to date, and 60 PocketQubes up to date. So you can see here an example of a 0.25 CubeSat, which is the Space B developed by Swarm Technologies. And here you can see the FOSSASAT-2 Lite platform that would be launching within the PICOBUS mission. In this image, we have tried to compare different aspects of the satellites to see if there is an optimum solution for this kind of applications. On the one hand, regarding the power, this kind of satellites can generate up to 2 watts. Let's consider that each solar cell generates 1 watt. FOSSASAT-2 Lite just can generate up to 1 watt. But on the other hand, we have FOSSASAT-2 Evolve, which is an evolution of this design that will carry on deployable solar panels that would let us generate up to 9 watts. Following with the comparison, we have the attitude determination and control system, in which the Swarm Space Bees are mainly based on magnet torquers, same as FOSSASAT-2 Lite. And on the other hand, we have the FOSSASAT-2 Evolve platform that would carry magnet torquers and reaction wheels. Magnet torquers would be used in order to desaturate the reaction wheels. And we are working on 2 different possibilities, one with 3 reaction wheels and one with 4 reaction wheels in a pyramidal distribution. Another key aspect that we consider while doing this kind of mission is the possibility of hosting extra payload space. We assume that the 0.25 CubeSats don't have enough space to have another extra payload. In the case of FOSSASAT-2 Lite platform, this space is below 0.5 Ps, and in the case of FOSSASAT-2 Evolved, the extra payload space is around 1 P and 250 RAMs. And finally, regarding the launching cost, in this case, launching CubeSats or this kind of CubeSats would be cheaper than launching PocketQubes. Another advantage of this kind of CubeSat is that it can fit to fill in gaps in deployers. For example, imagine that one university has developed a 1.5U, then you could fill the gap with this kind of CubeSats. And on the other hand, we have with the current launch opportunities that launching these 2P PocketQubes would be at around 35,000 euros. So as you have seen before, it seems that FOSSASAT-2 Evolve platform is such a good solution to optimize the power generation, the control, and the extra payload space. As Julian mentioned, we are really encouraged to see in more detail the technical dataset that is publishing in the website of the workshop. As I mentioned, the power generation is up to 9 watts with the solar panels deployed. The attitude determination and control system is active control with 3 reaction wheels and the magnetorquers in order to desaturate the wheels. The downlink data speed is up to 0.25 megabits per second in UHF. We have, as I mentioned, the payload volume up to 1 P with 250 RAMs, regulated bus, 3.3 watts, maximum power peak tracker, 4.5 watts hour for storage, solar panels, and 512 megabytes on board memory. And our objective with this platform is not just to let people to prove their technology or their payload, but also to provide our own services with IoT. So now let's have a look of constellation based on this kind of platform. The key objective, as you can see, is to maximize the coverage, minimizing deployment time and cost, which is intrinsically related to new space paradigm. The study case, as I mentioned, is low power and low latency application, which lead us to perform IoT services in narrow band. And here in this graph, you can see the different launch opportunities. As you can see, we will focus on these 4 type of orbits, which are synchronous between 500 kilometers and 550 kilometers. PocketQubes launched from the International Space Station at 400 kilometers, and PocketQubes deployed from Cygnus spacecraft at 500 kilometers. If we put this kind of orbits in our funnel, then we have our final goal, which is the constellation. In order to deploy the constellation, we will make use of our PocketPod. As Julian mentioned, there are still lags in the launch opportunities regarding PocketQube, so we assume that PocketPod is a really good option to launch your PocketQube. It has an 8P capacity. For example, in this case, we could launch 4 FOSSASAT-2 per pods. The objective is to launch multiple PocketPods per launch. This is the Vigoride platform developed by Momentus with all these deployers inside. And the cost will be reduced up to 18,000 euros per 1P. As Julian mentioned, PocketPod can be integrated vertically and horizontally. And now that we have the tools to deploy our constellation, we have to focus on which kind of constellation that we have with the current opportunities. This is an example of a constellation composed by 48 satellites divided into 4 planes, and with 12 satellites per plane, which is similar to launching 3 full PocketPods per launch. I don't know if you can see, but for example, this constellation is formed by 3 sun-synchronous orbits, 1 dusk dawn, 1 high noon, and 1, let's say, Earth observation with an L10 of at 1030. And this is the expected satellite distribution after performing the maneuvers of differential drag. The 12 satellites would be optimally separated around 30 degrees each. So we know how we won the constellation, but let's now discuss how are we going to reach the optimal distribution of the satellites. And the key lies on the attitude determination and control system. We will use the reaction wheels to change the relative position and the attitude of the spacecraft. We will have the minimum drag configuration and the maximum drag configuration with the solar panels deployed. And by changing the ballistic coefficient, we would be able to separate along the orbit the different satellites. In this plot, you can see the orbital lifetime. It's a parametric simulation considering different ballistic coefficients. Let's forget about these cases because too optimistic. It means that they are flying always with a minimum drag configuration. But as you can see here, the lifetime of our satellites would be between 1 year and 3 years, more or less. That will lead us to be following the technological developments in order to be continuously launching satellites, and each time the satellites would be technologically better. Finally, this is one of the figures of merits of the constellation. It's related to the revisit time. With this kind of constellation, where you can see some gaps, we arrive to this revisit time. This graph means that the 50% of the times the revisit time would be below 5 minutes. The 90% of the times the revisit time would be below 8 minutes. And the worst case scenario would be one case in which the revisit time would be 1 orbit, would be around 95, 97 minutes. So that's it. Don't forget that PocketQubes recover the initial spirit of CubeSats. FOSSASAT-2 it's an inexpensive, reliable, and flexible solution for IoT services. The PocketPod lead us to decrease a lot the launch cost, and we are aiming for a constellation to be anywhere, anytime. Thank you so much for your attention. Do not hesitate to contact either Julian or me if you have any questions. Thank you very much.
So does anyone have any questions for Vicente? If not, we shall be moving on to our next presenter.
Okay, fine. So thank you very much, Caio. Hope to see you soon. Bye.
Nice seeing you today. Bye. Next up, we should have Sajad. He'll be presenting soon. Yes, here he is. Hello, Sajad. Are you able to hear us?
Hello. Can you hear me?
Yeah, we can hear you fine. Would you be able to share your screen?
Let me share my screen. I can't see the sharing. Okay, I found it.
Getting some support from Alejandro.
Okay. Can you see the screen now?
We can see it now, yeah.
Okay, let's start then. Hello, everybody. I'm Sajjad Kazanfania. I'm going to talk about the Homage project, a multi-purpose constellation for PocketQubes. So I'm representing the team. I'm founder of FOSSASAT-1, I'm a startup on space education and outreach. And we do have some projects on education and engineering and entrepreneurship. And as you can see, Homage is one of our orbital projects. In this project, I have 3 false run, Vahid, Amiran, and Reza in electronics, communication, and software. And also we have a great team from Argentina, heading by Alejandro, as you may know him much better than me. Alejandro is the founder of Space from Argentina, and we do collaborate on this project with each other. Okay, in this presentation, I'll go over very shortly on PocketQubes, then I explain the Homage project and the progress, and then I will prepare the overall plan that we have on this project for the future. So as you have heard a lot this day, and you know much better than me, PocketQubes are very close to CubeSats in the space industry, but they are now in a much more affordable case, and also they are not only a good platform to be used for education in environments like university, but they are a very good option to be used for starting business in new space. So based on that, we started a collaborative project called Homage, a miniature project to administrate joint innovation. This project is out of a collaboration with Space and FOSSASAT-1 with 3 main goals. The first is to test in orbit the very first step of forming a constellation with intersatellite link. The second is to try and test IT mission supporting from space based on LoRa communication, as many of PocketQubes are doing it. And the third is to bring a new approach for making space more accessible, mainly for space emerging countries like Iran. So based on these aims, we started a sketch for the Homage. Homage is made up of 3 main satellites. The first is Mother, 1U CubeSat, which is going to deploy 2 other satellites, 2 PocketQubes called Boy and Girl, in order to form a constellation for IT mission in orbit. So after deployment of these 2 PocketQubes out of the Mother CubeSat, there will be both IoT missions and intersatellite link between these satellites. The PocketQubes are only to receive the signals on LoRa communication based on the LoRa modules that are going to be used, the same as the one is in FOSSASAT-1, and they are going to save them and transmit them regularly in ISL band to the Mother CubeSat. So the whole data will be transmitted to the ground using the CubeSat Mother. So this platform could be used for training our new and next generation fellows in the team. And also we are going to use it as a platform for innovation management, or also make it as an opportunity to help our fellows for entrepreneurship and sharing market between 2 countries in collaboration. As you can see, this is the overall design of the CubeSat model. The CubeSat model is going to be in 1U extended size based on NanoRacks deployer. So we are going to use the extended cylinder, which will be inside the spring of the deployer. And after deployment of the CubeSat will start deployment of 2 PocketQubes. To make it more tangible, you can see the overall mission simulation. As you can see, after the CubeSat is commissioned and we can control it safely, the deployment of 2 PocketQubes starts. So the 3 satellites will start operation in one orbit that will increase the amount of supportable ground stations on Earth for IoT mission. So it is predicted that the distance between the 3 satellites would not exceed more than 5 kilometers during the mission life that we have considered for the satellites. The project was announced in June 19, and it is not so much late after that. We started to accept proposal on the subsystems of the CubeSat and also PocketQubes. Then we are going to build engineering models and develop the flight models after that. And it is anticipated to cover these models in a period of about 6 to 7 months. So this fast-paced project is needed to be controlled very carefully. To go over the design of the PocketQubes are in 1P configuration, and based on the system design, the ISL is going to be on the base seat and close to the patch antenna, which is going to be placed on the outer surface of the base sheet of the PocketQube. After that, the power board is close to the ISL, the most power consumer part, and obviously will be after that on the next layer or board close to the LoRa. LoRa will be on the top, and it will be close to the antenna that we are going to deploy in orbit after the release. So the structure will be in the form that you can see in the 3D print model here. And we are anticipating that we will have a one-sided communication from LoRa ground station components and two-sided communication between the CubeSat and the PocketQubes in S-band for ISL and delivering the data from PocketQubes. To go forward, there is a single bus for electrical power supply and also intra-board communications. The electrical power supply is based at 3.3 volt main bus, and we have considered a small lithium polymer battery for it, and also the communication between boards are based on I2C, so we have some kind of processing units in each board to handle the other communications. The LoRa is based on FOSSASAT, the inspiring PocketQube that we all know about it, and we have some changes in the software in order to receive up to 255 signals from other LoRa transmitters and handle them through one line. And after that, we are going to transfer the data saved on onboard memory to the CubeSat to be transferred to the ground station and then servers by ISL based on XP protocols and using COTS. For the CubeSat design, I should say that we have separated the CubeSat into three main sections, and two of them are for CubeSat platform. The former is 2 gigabytes in 84, 110 by 21 millimeters, which hosts the communication module and EPS. Communication module integrates the ISL and IoT payload. As you may know that the CubeSat itself owns the LoRa communication module too. And also the EPS is made up of lithium-ion batteries, and also integrates the PDU and VCR and BDR units. There are two smaller boxes to host OVC and also the payload, main payload of the CubeSat. We are going to test the main payload of this project based on LoRa communication to increase the number of the units which can communicate to the CubeSat, more than 255 that we have already achieved. And also the third part of the CubeSat will be PocketQube deployer, which is very close to the PocketQube deployer design that Orbital has presented, with some changes in the, as you can see, with some changes in the edges to conform to the cylinder that NanoRex lets us. Okay. In the shape, you can see that the bigger box are in gold, black, and the smaller box are in gold. So the next step was to go for ground station. We have developed two types of ground station in hardware. The first is the one that can be connected to the PCs, so the use of them would be very easy. The same as some kind of ground station that have been presented in previous presentations. We are using some kind of typical antennas used by TV in UHF or something like that, with some changes in the impedance of the receiver. And with this kind of antenna, we can receive different signals in UHF. And based on that, we may use the same VHF antenna that were used by TV or radio stations in RF for CubeSat communications. Also, we have developed another kind of ground station which can be used by PocketQubes or CubeSats. This kind of ground station is typically in handset hardware form, and the handset not only has itself small LCD which can show you some raw data that you have received and can be controlled with some low functional keys based on the thing that you can change it through the mission, but also can be connected through a OTG cable to the smartphone. So the smartphone has an application that we have developed now on Android. So the Android application can be connected to the ground station hardware, so you can control the satellite or follow it on orbit, or see the graphs for any parameter that you have selected to be monitored during the flight of the satellite. Also, you can provide this handset as a tool to be used for IT services. So this can be used as a very simple interface to be attached to the sensors, which we are going to share the data to the satellite. Another part of the ground station is data server that is going to handle the data that we have received from the CubeSat or any other satellite in the future versions and generation of the constellation, and will provide us a UI to generate some services for our users. To provide an update, we had a live show presenting the Amash satellite, and you can see that our fellows were working in their homes because of COVID-19, we are working remotely. Still, we are working remotely, and we have some sessions, online sessions with our fellows in Iran and also our fellows in Argentina, who are in charge of deployer and also a PocketQube. And to go for future plan, I should say that we are not going to just make some PocketQubes or implement some design into the products. We are going to provide some solutions in order to get to business and to some businesses. So we have considered to organize a competition on Pico satellites, mainly PocketQubes in Iran, or in order to engage the whole students and who are interested in small satellites, especially on PocketQubes, in order to make the ecosystem. And to do this, we have some supports for them on education, also and networking and marketing. And there are also some kind of funding and investment in some cases that we find them profitable in future. To go for our plan, we are working on platform mindset. We are going to provide some platforms that could be used for different kinds of missions that we are going to develop. Also, may other use our platform, like the one that other fellows are developing. Also, a project called PICOBUS is going to be done. We are going to work on PocketQube on a board to summarize the platform on a board. And also we are developing our technology management system based on IT-based solutions that we have used through the COVID times, and we are going to make it as a service for others. Also, in a business side, we are going to provide some solutions for on-orbit testing and demonstration for anyone who is going to test its components in orbit, and also some services for newcomers. That it was the thing that we lacked, and we lack now. We wanted to test our ground facilities using some satellites in orbit, but we couldn't find any. And also the other thing is to guide the next generation member of our team to provide their businesses on subsystems for sale. You can see a very early image of our ground station software on PC, that there are different parts that we can collaborate with different fellows in this workshop, and also others who you may know that we can collaborate with. And we are start, and we are open and excited to contact with anybody in this workshop and future opportunities to collaborate on the PocketQube projects, basically on a space or on the Earth. Thank you for the time, and you can contact us using these emails, or you can follow us on Twitter or on Instagram at FOSSASAT-1. Thank you.
So does anyone have any questions before we move on to our next speaker?
There may be some.
So it looks like that's a wrap for Sajad. Good presentation. Thanks for coming today. And next on, we've got Mateo from Porkchop Space, who are working on PocketQube propulsions. Would you be able to share your screen with us?
Yeah.
Absolutely. So can everyone see? Can people see my screen?
participating on it. It might just be lag on my side, so I don't know if anybody else can.
I think I got disconnected. Can
I can hear you. Okay, there we go.
Okay, great.
Great.
Before we begin, I'd like to thank you, Kais, very much for having us over and for organizing this great event. It's our first time being here, but we're looking forward to many years of being present. So as you said, we're Porkchop. We build propulsion systems for PocketQubes. We haven't prepared a PowerPoint, we've prepared a video instead. So without further ado, I hope that everything will be audible and visible, and here it is. We get the question, where does the name Porkchop come from? A lot. During the Voyager era, NASA started to create these plots when planning interplanetary missions. They wanted to see how much propellant would be required if the spacecraft took off on a particular day and arrived on another particular day. By putting the launch date on the x-axis and the arrival date on the y-axis, you get these funky contour plots, which the engineers at NASA decided to call Porkchop plots. We think these psychedelic plots are the perfect representation of old space. Complicated, clunky, and uninspiring. And the name Porkchop comes from the idea of asking ourselves, how can we make this simpler, but also better? We constantly ask ourselves this question at all stages of the design process. And today, we're really excited to show what following this design philosophy has allowed us to create.
Much like the rest of the PocketQube community, Porkchop started as a passion project. We are three guys who care deeply about the future of space exploration. Our home is Stockholm, Sweden, where we all met in college.
Just introduce yourself, it's for the video.
Okay, so I'm Bertza. I'm working at Porkchop as the head of electronics and control. I'm still doing my master's in digital integrated systems. I worked with powers of Nike back here in Pakistan for almost 2.5 years. Yeah, currently working with another startup called Stockholm Water Technology as a data engineer. Hi, my name is Nico. I'm from Mexico. I did my bachelor's in mechatronics and I just finished my master's in aerospace. I had some experience working with CubeSats. There's this project in PICOBUS. I was there working as a ground station developer, but also I did my thesis designing the mission operations in the propulsion system.
Hey, I'm Matthew Milanovich. I'm the head of structures and interfaces at Porkchop. My background is in mechanical engineering and in aerospace engineering. I've worked on some really cool R&D projects at Ericsson in the past, and more recently, I worked at KTH Hybrid. We're developing a pod that will travel faster than this metro is right now. Also, in free time, I like to ski, and I don't have a lot of free time.
The thing which has really brought us together is our shared vision. We want to enable affordable space exploration for everyone. When we first came across PocketQubes, we were overjoyed by the fact that there are so many of you out there who share our vision. affordable space exploration for everyone. And we believe that the desire to explore is such a human one. And our goal at PorkChop is to give PocketQube developers the tool to explore space affordably and profitably.
We've been asking ourselves, how can PocketQubes be made even better than what's out there today? How can we take advantage of the fact that PocketQubes are able to provide many of the same functionalities as CubeSats, yet still work around the small size constraint? Some of the drawbacks PocketQubes face today come from the fact that once they're deployed in orbit, they're stuck there. And this really limits the lifetime of PocketQubes and limits how much PocketQube developers can achieve in a single mission. It also means PocketQubes can change their orbit throughout their mission, avoid collisions, or perform orbit phasing. And we know, of course, that a propulsion system has the ability to solve all of these problems. Since becoming increasingly widespread among CubeSats, propulsion systems have been enabling longer lasting and more exciting missions. Now it's time for the same thing to happen to PocketQubes. Today, we are extremely excited to announce what we believe is going to take PocketQubes to the next level, PorkChop X. PorkChop X represents the ultimate propulsion experience for PocketQube developers. PorkChop X replaces the structural frame inside PocketQubes, adding propulsion to your PocketQube without taking up any payload volume. We call it invisible propulsion. All of the electronics are embedded right inside. Let's compare this to existing propulsion solutions. Traditionally, propulsion systems have taken up significant space inside the PocketQube and have required an entire side of your PocketQube be completely empty. PorkChop X has a structural frame made of anodized aluminium. We wanted to maintain the same exact mechanical interface as current structures, including a feed-through hole in the middle. PorkChop X has a 10 by 12 millimeter hole, meaning users have the freedom to pass cables for antennas or sensors through PorkChop X. We've also added optional flanges for PocketQubes, which have deployable solar arrays on top, capable of holding even the largest of solar arrays.
Another huge problem with existing propulsion systems is that they come with a single thruster which can only point in one direction. If this single thruster malfunctions or has any sort of defect, the entire propulsion system is rendered useless. It also means that if the thruster is in any way misaligned, then there is no way to correct this when firing. For these reasons, PorkChop X comes with 8 thrusters in total, 4 main thrusters and 4 redundant ones. By adding dual redundancy to each of our thrusters, we are confident that PorkChop X will be able to operate properly during its lifetime. What excited us most about including 8 thrusters right out of the box is that it now allows PocketQube developers to perform attitude maneuvers in 2 axes using PorkChop X, to desaturate the reaction wheels, but also to let them easily compensate for any possible thrust misalignment when firing. Better yet, when you run out of propellant in the main thrusters, you can make use of the redundant ones for the rest of the mission. PorkChop X uses vacuum arc thruster technology, which is perfect for PocketQubes. It can operate on very little power, and it uses solid metal fuel, so you don't need to worry about any leaks on board your PocketQube. Vacuum arc thruster technology works by consuming one of the electrodes when firing. When enough voltage is applied, the solid mass almost instantaneously becomes a fast-moving plasma, providing thrust to the PocketQube. PorkChop X also doesn't use any ITAR materials, so transporting it is easy as pie.
Now let's talk about specs. You would think that, well, those guys at PorkChop have spent all their time packaging all of the electronics and thrusters inside such a tiny package, so there has to be somewhere where they cut corners, right? Well, not quite. PorkChop X is completely designed around the thrusters, because we wanted to blow you away. We wanted to be extremely confident in the data we presented, which is why we fired Porkchop X thrusters over 500,000 times during testing. Each thruster on Porkchop X delivers 3 micronewtons of thrust, meaning you can get up to 12 micronewtons of thrust when firing all 4 main thrusters. Another key performance spec is specific impulse, or ISP for short. Porkchop X thrusters have an ISP of around 4,000 seconds, which translates to very efficient use of fuel. Now let's have a look at how Porkchop X can boost your PocketQube. Porkchop X can provide up to 35 meters per second delta V for a 2P PocketQube, or up to 23 meters per second for a 3P. Using all this delta V, let's take a look at some of the great things you can do with a Porkchop X. Currently, PocketQubes have an estimated lifetime of around 2.5 years orbiting at 500 kilometers, or 2 years, 8 months for 3P PocketQubes. Porkchop X lets you extend the lifetime of a 2P by up to 1.9 years, or by up to 1.3 years for a 3P. How cool is that? Who would have thought that up to 76% longer lifetime could be achieved by simply swapping out your structural frame with a Porkchop X? Now let's say you want to use Porkchop X to deorbit. Porkchop X allows 2P PocketQubes to descend by up to 64 kilometers and 3Ps by up to 42 kilometers, shortening deorbit time to just 14 and 15 months respectively. Porkchop X is opening up a whole new spectrum of possibilities for PocketQubes, and we are so happy to be the first to offer attitude maneuvers for PocketQubes using a propulsion system. Porkchop X will be available for sale in December 2020, starting at just $59.99.
Porkchop X is really power efficient. We have achieved these really impressive performance specs, all while consuming only 600 milliwatt per thruster, or up to 2.4 watt when firing all 4 main thrusters. Porkchop X currently works with a 5-volt power input. However, we can easily scale this up to 12-volt or 24-volt rate. Porkchop X receives commands from onboard computer using I2C. It's wonderfully simple to operate, and we really think that you're going to enjoy using it. We even managed to squeeze some sensors inside, which gives users data when monitoring the health of their Porkchop X, giving you full control at all times. We have also baked several fail-safe mechanisms right inside, which ensures that your mission is never compromised, no matter what happens. Porkchop X is truly the ultimate propulsion experience for your PocketQube.
But what really excites us is the new missions that you, the PocketQube developers and enthusiasts, will dream up of. Whether it's for Earth observation, IoT, or deep space missions, we want to be right behind you, giving you the push you need to get into the orbit of your dreams. And there's a really nice quote which summarizes how we feel about producing the best possible propulsion systems for our users. We always believe that if you give people wonderful tools, they will do wonderful things. The next step in our plan is to gain space heritage. In February 2021, the first ever Porkchop X will be launching on board Laika, a 2P PocketQube built on FOSSA Systems' FOSSASAT-2 platform. This mission will give Porkchop X space heritage, as well as allow us to make further design improvements based on all of the lessons we'll learn.
We've learned a tremendous amount from working with users such as FOSSA, and our door is always open for people who want to reach out to us about getting propulsion in their PocketQubes. We want to hear any ideas, comments, or suggestions people have on how we can improve. We are also aware that many PocketQubes today follow different standards on the inside, so we are very open to working with each individual user to make a customized Porkchop X for their particular needs. Finally, we will be hosting a live Q&A this Saturday on YouTube at 6 p.m. Glasgow time, where we'll be answering any questions you might have and getting to know you. We hope you'll join us. Despite being continents apart and restricted by COVID, we at Workshop love the fact that we are all united in our common goal to explore space and develop truly wonderful nanosatellite technologies. Thank you and have a great PICOBUS 2020.
So as Victor mentioned, we will be hosting a Q&A on Saturday after the PocketQube event is over. So we'll be ready to take any questions that people might have. Just talk with you guys. We're probably thinking of grabbing a beer all together, so it's very formal and we're gonna have a lot of fun. So I'd invite anyone who has any further questions for us to join us then. Thank you.
That was a great presentation. I think everyone enjoyed the video, going by the comments. It was a good one. So that sounds exciting when you get your space heritage. If anybody's got any questions before we moved on, we could get that out of the way. Next up should be Massiage from Merb Space, talking about his 3D MSGE, but I've not been able to contact him, so we might need to go ahead to a break if he doesn't turn up soon. Hold on a minute. Mattia, are you still there?
Hi, yes.
You've got a question from an anonymous attendee. For the firings, is this continuous or accumulated in vacuum or atmosphere? For ISP, was this measured or calculated? Typically, VATs operate in the 800 to 1300 ISP for common fields, and 4000s is seen more in VIITs.
Sure, I was just typing the response. To answer, the firings are accumulated over several tests, each one lasting anywhere between 7 or 8 hours of fully continuous firing. One of the steps we plan on doing after lessons learned post-launch is to do even longer longevity tests. I think 500,000 of firings is definitely cool, but we want to be in the multi-million firings. Regarding ISP, this was measured. We bought a very small, I think sub-milligram scale where we measured differences in the thruster before and after firing for several 100,000 times. And from this, we compared all of the ISP values. 4,000 seconds was the average that we got. We had some where we would have even more. Sometimes it would be in the 3,000, high 2,000s, 2,700. So that's based on measured values, not just theory. And yeah.
So I've heard back from our next speaker. He's just taking another kind of couple of minutes to connect. There we go.
Hello, hello, can you hear
Hello,
me?
how are you doing? Good to see you.
Hello, hello, good to see you. I'm sorry, today I'm calling from my car because I was just on a meeting which took a little bit longer than I expected. But you know, life is short, so don't waste time more on this, and let's move on to my presentation here. All right, how can I share my screen here? Oh.
There should be a tab at the bottom. I don't know if you can see that between chat.
Okay, share screen. Yes, that's true. Right. So, okay. Right. Okay. Can you see it? Big logotype of my company here. Hello, my name is Maciej Urbanowicz. I represent the MERP Space company, and I'm from Poland. Today I'm talking to you from my car because I just left the meeting with my customer, and we were talking, of course, about space and the space debris mitigation issues. But today we are not going to talk about space debris, but how to make a debris in the future, for sure. So I'm gonna present you something about how to implement processes in a very cheap way to your projects. So my presentation title is the 3D MGC, more efficient mass production of small satellites by implementing the process optimization approach. And this is something quite interesting in the perspective of small satellite vendors and evolving market of small satellites in the world. And of course, PocketQubes are small satellites, so why not talk about PocketQubes as well here? Satellite development process looks quite interesting to me because it merges all the different aspects of different projects from different industries. We're talking about hardware manufacturing, we are talking about software manufacturing, we are talking about integration of different things together in one small tiny box. So every kind of satellite in the world is made in a very similar way. First of all, we have an idea. So we need to figure out what we want to do. Then we define the mission statement, mission definition. After that, we know what we want to do. So then we create requirements definition. And this is the long list of requirements where we then translate them to the design. We design the satellite, design the simple, small parts, we design more complex parts, we design the whole system. Then we assemble it, and then we test it. Finally, we launch it to space. So it looks quite simple, just 9 steps. But today I'm not gonna talk about every step here. I'm just gonna focus on 3 things: requirements definition, assembly, and a design. Requirements definition is another sub-process to the main process. And of course, here you have everything simplified. But let's think about the main steps you have to do in order to make your mission. In most cases, you need to think about the business needs. Of course, if we are talking about scientific missions, that's another story. But scientific missions are also business-oriented somehow, because in the end, you want to get something from this mission. So you define the business needs, what you want to achieve. Then you analyze this business needs, and you need to figure out what you can do and how. You define requirements, what you would like to achieve, your goal. So business needs defines the outcome from the project. You define your goal, it's just a basic driver for every project. So this is the very first step you need to do in order to make a mission. And why I'm talking about the process, because sometimes, and frankly speaking, I made that quite often in space industry because I provide my services not to the space industry only, but to IT and to industry, to manufacturing industry. They think in a process way, but in space industry, that's another story. And I found that many companies in Europe and in the world don't think about space as a process. So you need to analyze everything in order to get your results. Once you analyze your business needs, you can create a list of requirements, and then requirements translate business needs to clearly defined rule about something that has to be done. And there is no room for interpretation. You just can't interpret the requirements. You need to clearly define them in order to translate them. Again, translation of the requirements to the matter, to the physical thing. It can be, of course, virtual as well, but software. But when we are talking about the matter, we are talking about the hardware. So, for example, we would like to decrease the time and cost of delivery of goods from point A to point B. And yeah, there may be many ways how to do that. So we need to break this business needs down to single and simple things. So, for example, we need to show somebody, for example, the delivery man, the UPS, for example, or FedEx, how can we implement some tools and what kind of tools? In our case, perhaps maybe navigation system, GNSS systems. So we define the outcome. The outcome would be that the guy would have some kind of terminal which can show the way how to get from point A to point B in a very efficient way. We start then designing the system. So we are breaking down the requirements, and based on that we make feasibility studies and we design the system. We design something which turns to something that we are going to produce in the near future. So this is our outcome. And once we design the system, we start developing the system for testing purposes to verify whether we are able to make that in the future or not. So in the design, we need to define a few things. First of all, feasibility studies. They give us the high-level design of the system. There may be multiple solutions, of course. We need to define the tools required to move forward. And this is very important, feasibility studies. Sometimes people say that's a waste of money. But trust me, I just did that a few days ago. The day I had a meeting with my customer on that matter. So we were discussing my feasibility study I did for them. And this is a key driver to them because now they know what kind of resources they need to assign to this project to move forward. And they are able right now to spend more money on the thing that they thought should be right. But I gave them a proof that this is right. So this is a very important step. And once we finish that, we can start working on translating these requirements to a matter. So we find the technical solutions. Then we develop something. Right. So we need to explore technical solutions, requirements, implementation to build a system which helps to deliver goods quicker at a lower price. So that was our goal. And as I mentioned before, we use GNSS system and IoT. This is the result of our feasibility study. Okay, move forward to another topic, assembly. And this is also another sub-process. Assembly feasibility preparation, a collection of all required parts, execute the process, and assembly verification. These main steps of the assembly process are key to build your system. And just in a few minutes, I will talk more about the optimization, the main topic of this presentation. When we are going to assemble something, we need to collect or require tools. So any kind of tool you think you would need. Okay, I mentioned that. I said that, okay, you may think that you need something, but what do you really need to build your satellite? What kind of tools? You need to foresee in everything. You need to build a storage facility. You need to create an assembly environment. Then you need to correct all required parts to build your system. Of course, it would be great if you can have all of them in one place, so you don't need to wait for any other vendor to deliver the goods for you. Then you execute the process. And here we have a very interesting thing, because how are you going to assemble your satellite? Are you going to assemble something like Lego bricks, so take a random brick and try to match with another part? Or do you have some quite well-defined procedure how to do the thing? And the assembly verification, once you assemble your device, your satellite, you need to verify how well you did that. This is the very last step that you do when you do assemble the thing. So when we look at the examples, how we prepare our facility, we need to build the assembly facility and use our required tools. And what kind of tools we need to think about them when we are working on the assembly procedure. For example, MJSEs, so power supply, screwdrivers, wrenches, and all of this stuff. We need to collect all of required parts, so all of your ADCS, computers, solar arrays, and so on and so on and so on. So you need to be prepared to store them in required conditions. And of course, then we execute the assembly process when we assemble the satellite itself. Right, so process optimization. I went very quickly through the main steps of the business analysis, requirements definition, and assembly of the satellite, and the design of the satellite. So what the process optimization means. It is something which lets you cut your cost and time with keeping the same or even better quality. When I was talking with a few companies at conferences about the process optimization in space products development, they were very, I would say, they were not very happy about work process, because they thought that it's very expensive, because they thought that when they implement the process, it would take a lot of money and time to implement the process approach. However, you don't have to implement process everywhere. You don't have to make things complicated. I will give you a couple of examples. For example, when you design your case for batteries or the satellite case, so it's just a box. How many types of screws are going to use there? When you design that, you may think, okay, it just doesn't matter, because it can be M3, it can be N4, you can mix all of them in one device. But when you start thinking about the manufacturing process, it matters, because the guy who is going to manufacture your thing has to collect all of their tools and even purchase additional tools just to make this one different hole and to make that thread, because this is your requirement, but is this requirement really good? So that's the question. So when you start thinking about the process optimization, you don't only think about yourself, how do you do that thing, but you think also about the others. So speaking of which, for example, about these holes and threads, when you can unify all of the holes and threads in your device, it simply cut costs. It simply cut time, because you can save the money, you can save time, because the guy who's going to manufacture the thing for you doesn't need to go to a shop to purchase another tools just for your needs. Of course, if you absolutely need that, there is no way you have to do that. But if you don't need that, it is good to oversize a little bit your case. Couple of another hints. Yeah, I mentioned the example about the threads, but what about building a modular software? I also provide services to IT industry, and it's very common to build very modular software, because it's then way easier to modify the software for future projects. So in case of software for space applications, if you can build a modular software, you can make a quick integration with other missions, because qualification of the software for space missions is quite complex and takes time. But once you prove that this part of the software works, it can be easily integrated with another mission. And of course, the testing will have to be done. However, it's way easier to do that if you once prove that it works well. Another example, you can use the same connectors. So I experienced a couple of times that different manufacturers, different vendors of space parts, of space components, deliver parts which are not compatible together. And I'm not talking about, for example, CubeSats or PocketQubes just, but let's think about connecting solar arrays. Let's think about connecting some sensors and so on. There are a bunch of connectors widely used in space industry, but once you can unify them and you can just maybe use one or two types for your mission, it's simply better because you cut costs. It's easier to assemble the satellite. So by process optimization, I mean looking for these small things which can make life easier. You don't have to build the whole big process. And of course, I can help you to build that because I do that quite often. However, just think about the small steps. You don't have to change everything. You don't have to implement the ISO standards. You don't have to implement the CSS standards, but you can just do one small step to make life easier. So fewer tools are required, shorter delivery time and better availability of components. This is very handy because you don't have to wait for a specific part weeks, but you can go and buy the very thing you need on the nearby shop. Another very interesting point, which I mentioned already, is mechanical design. What I suggest, and by suggest I mean I highly recommend, is to consult your mechanical design with technicians who will manufacture the part for you. And this is very important. This year and last year, I was delivering many components to my customers abroad, and there was a problem because they designed something which was not consulted with me. And yeah, I accepted this, and I accepted this order. However, it took me a lot of effort and money as well, and time to manufacture the parts to them because they didn't consult the designs with me and with my guys who actually are making things for me. And that was quite tricky to manufacture the parts because we simply have a little bit different manufacturing processes in our factories than the other vendors. And this is very important if you can talk with the guy who will actually manufacture the part for you, because then this particular guy, the specific guy, will tell you, okay, I will do that this way and I will not do that another way because, and he will tell you the list of reasons why he does it this way. And it really saves money and time, so you don't make obvious mistakes. I mentioned about the M3 and M4 threads, for example. That's one example, but I had an experience when my partner, my customer, wanted to make some very specific shapes in the material. And from the business perspective, from the engineering perspective, and from the mission perspective, it was completely not necessary to do that because they're not going to use that particular thing in their mission. But somebody at the company decided to design this thing this way, and it took us twice as much time to build the thing. So this is a small optimization of the process, of the design process. So you can consult with your technicians how to make things. And of course, it's very easy then to maintain the quality of your products. So the parts are very easy to manufacture. And another thing is to use the right tools. So use NGCs and EGCs, which then can help you a lot when you build your satellite. So process optimization, we can summarize part as quite a simple thing, because when we build anything, it should be simple. So first we need to identify our needs. So for example, we would like to make a delivery chain shorter, or we would like to cut the cost, or we'd like to cut the time needed to build a thing. So we need to clearly identify our needs, what we would like to get from this process optimization. Then we cooperate with all stakeholders to talk about how to do that. And again, don't spend too much time on that. Just try to make things simple, 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 simple. Then optimize it. So once you talk with everybody, once you identify your needs and you know what you like to get, then you can optimize how we work. So I gave you a couple of examples. And finally, we have a successful story of making things better. Yeah, okay. Mechanical grade support equipment. My company, Marble Space, offers MGSCs dedicated to small satellite vendors. And today I'm gonna also present you 3D MGC and 1D MGC, which are my main products. We have two MGCs, 3D MGC and 1D MGC. The 3D offers the 3 degrees of freedom, 1D MGC offers 1 degree of freedom. And of course, there are possible different configurations. They are dedicated to CubeSats and PocketQubes. And here you have a picture of 3D MGC, which lets you freely rotate your satellite around 3 axes. So 1D MGC, you can rotate the satellite around 1 axis. Why is it handy? When you work with a satellite, you would like to avoid making any damage to your components, to your parts. So you would like to you like to make things safe for your satellite. So you don't want to drop it, you don't want to destroy the parts. So that's why it's very handy to use some jigs and rotating tables, or like 3D MGC, this special adapter where you can put your satellite and then rotate the satellite around 3 axes. So when you are going to assemble your satellite, you don't have to make things danger to your parts. For example, if you deploy the solar arrays, you are not worried about dropping them because you just have slippery hands with your protecting gloves. So that's quite handy. And I'm gonna present you the short video. I hope that it will be visible here. I don't know if you can see that. I hope yes. If not, just visit my website, so you'll be able to see the video. The 3D MGC is designed to handle all of the satellites as well. The 1D MGC, you can see how easily you can rotate your satellite around 3 axes, and you can reduce unnecessary steps in your assembly process. So this is the process optimization. You simply remove the steps that may cause problems. So this video shows the 3D MGC, but 1D MGC works in a very similar way. We can design all mechanical interfaces you need to use with your satellite. And we can help you also with making the assembly process better and more efficient. You can learn more information about the technical details on our website. And yeah, what you need is what you get. Okay. Another thing is for participants of PocketQube workshop, there is a special discount. So use the hashtag PocketQube 2020 code when you write to me. The special offer is valid until 16th of October. So I hope that somebody will be interested. At our company, at Merpspace, we offer business development services, bespoke development services, and manufacturing services. So head over to our website to learn more. Okay, the time is almost over. What you need is what you get. Thank you so much for your patience. Thank you.
Thanks, Maciej. So has anyone got any questions? I'll check the YouTube stream, see if there's anyone there. That looks like it's us until the break. Next up,
yeah.
we've got Alejandro Padero with InnovaSpace. So that looks like an interesting presentation to tune into. So we'll see you guys in half an hour.
Thank you.
Bye.
Thank you. See you soon. Bye.
Hello? I cannot hear you. Guys, your mic is off.
Good. Okay, so connectivity is good. Is your video okay?
Yes, my computer is working. Yes. Yeah.
Okay, that's good. So we've got you sorted. All right, we'll see you after the break then.
Okay, perfect. Is it okay not to use the webcam just to present our PowerPoint?
Yeah, of course, whatever you're more comfortable with.
Okay.
All right, cool.
Perfect.
Bye.
See you later.
Hello, Caius.
Hello, Alejandro.
I am ready.
Alejandro will be presenting on the PocketQube MDQSAT-1A, Design and Development of IoT Constellation for Agriculture. So, on you go.
Perfect. I share the screen. You can. I don't have the share screen. Ah, here. Sorry. 1 minute. You can see the screen. No? You can see?
People in the chat are saying yes. I think that might be to the past question, actually. Try moving it out.
Yes. Yes or not?
No, no.
No?
Oh, yeah.
Yes?
Yeah.
Perfect.
Sorry, my mistake.
No problem. Okay. Hello, everyone. I am Alejandro Cordero, CEO of Nova Space Argentina. Thank you for being here with us in the PocketQube workshop. First, thank you very much for this invitation to event today. Thank you, Tom and Caius and all the team of Arba Orbiter for giving us the space again for the second consecutive years. I invite you to know the future. This presentation I will talk about our PocketQube and MDQSAT-2P, design and develop of the constellation for agriculture. The contents of our presentations are introduction, system overview, power subsystem, onboard computer, communication subsystems, and future works. Okay. All started a year ago when I met with my friend in Scotland, and I could see that the future was literally in my hand. So since I came back from Scotland, I worked hard with my team to develop a ready platform to be able to bring IoT communication to the world. In this way, I want to tell you what our mission is about. The platform name is MDQSAT, elaborated by our company Innovaspace, and the name of the constellation mission is the Libertadores de América. Innovaspace mission is democratize access to IoT connectivity for everyone, starting with Latin America. We believe that with our satellites, we will revolutionize the Latin America IoT market. Our idea is tourniquet solution for agriculture in particular, moving from the end device communication, cloud, and dashboard for any application. Here you have some milestone. The first start activity with the amateur projects at Arduino with my students here in Argentina. And later the 2018 developed the first functional MVP Arduino. You can see in the picture. And we traveled with our team to the workshop in Scotland. And this year, 2020, we are accelerated by a Neutron, started accelerator here in Argentina by amount around $75,000 US. And this month, maybe in November, end of manufacture the first satellite assembly here in our laboratory. Sorry. In this time of the COVID, we have made many joint work agreements. In these reasons, have many alliance, for example, with Iran, with FASA, with my big friend Sahat, that talked before of me. The big project that the name is Project Amah. Sahat talked about it. The other agreements very important for us is, for example, Modke company, Brazilian company, developed our IDCS systems and have signed the agreement with a Porkshop for the propulsion system for the next generation of the MD CubeSats, and signed many agreements with the US company that provide the first launch for us. And this is a a recent news for, it's very happy for us. The state of Argentina subsidized for más de $250,000 and chosen the best technology project in our country. The plan for the next year is to launch the first satellite of the constellation of 100. Okay, let me show you our overview about general architecture of our satellite. You can see here a general block diagram. It shows the OBC as the center of the computer. Sorry, I can. That's okay. In the center of the computer, connected with a SD memory card, the S-band radio for payload communications, that you have electric power system, which has 3 solar panels and 2 batteries. You said a solar panel made for Azure with heritage in space. And you have a DCS control, VHF, UHF radio for TT and C, and other slot in case we need to add additional payload. Here you can see the 3D model of the engineering model, which will be assembled in the few weeks in our laboratory here in Argentina. You can see the future of our power source system. No surprise here. This power source system have the popular using SPB 1040, which has while used in previous CubeSat and PocketQube missions. So it is flight proven. Sorry. It has a standard 16-pin header, and that can be regulated from 3.3 to 5 volts. All components work with the Texas Instruments. This is very important for us. And it can handle 3.3 watts. This is a power source system. This is an analysis that we make. As for the power generation, we studied 4 different configurations of the solar panels. In the graph, you can see the mean power generation for each configuration according to the orbit. Because our mission will be fly as a big bag, we don't know for sure which will be the orbit parameters. And the power generation is strongly dependent on the orbits. So we simulated several sun synchronous orbits with the different local time of the sense nodes. The chosen configuration is the one drawn in the mesh, which can generate between 1.3 and 2.7 mean power. Onboard computer. Here is one of the many OBC that I think in our architecture. This is the family microchip, SAM-D, 32 bytes with standard PocketQube, have a magneto-resistive memory in all aspects. Your micro SD card slot have a magneto-resistive memory. In the communication have Texas Instruments insulator for all communications, you can see, and support all language for programmation, for programmer, sorry, the C, C++, Python, and Arduino IDE, maybe. You can see the shell of aluminum isolated. And communication subsystems, these missions will be count with the telemetry and telecom and radio and payload communications. The bands defined are VHF and UHF bands for TT and C, and S-band for payload communications. The shells are recomposed for rainy days aluminum isolated, and the other details are still in the definition process. Okay, the future works. Finally, let's talk about future work. As the part of the execution plan, we will develop the first low-cost IoT satellite architecture in Latin America to give access to satellite communications applied to the agriculture in essence. Our main challenge, milestone, you can see there, in 2022, finished a prototype primary test. In 2021, assembly all satellite and launch in the last of these years. In 2022, develop the 3 satellites of this platform for the trial and test. And 2023 launch these 3 satellites, and later in 24-25 launch of 10 more for the Latin American coverage. And maybe surely that one of our next step will be to open regional office in Peru, Chile, Mexico, USA, and Barcelona. This is the next step for the next years, sure. Thank you very much. Thank you for your attention. Stay here for any question. Cayos?
So does anyone have any questions for Alejandro before we move on? Thanks, Alejandro. It was a good presentation. So next up, we've got Michael Bretti from Applied Ion Systems, who are also working on PocketQube propulsions. He should be coming up soon. Hello, Michael.
Hey, can you hear me?
Yeah, we can hear you okay.
Great. So I guess I can just start sharing the screen. All right, just get this up.
Alejandro.
Can you see it?
Yeah, we can all see it.
Perfect.
Let's see. All right. My name is Michael Breddy, and thank you all for tuning in to listen to this talk, and thanks to Alba Orbital for this amazing workshop that they put on. Today, I'm going to be talking about my work on low-cost ionic liquid ion source electrospray thrusters for PocketQubes through my startup AIS. So for those of you who don't know me, I'm the founder of Applied Ion Systems. And as far as I'm aware, it's currently the only independent maker-based at-home R&D program for plasma and ion thruster development. So everything is done quite literally in-house and supported out of pocket and through donations through the AIS Patreon. And really the goal is to develop ultra low cost, easy to manufacture and open source thrusters, as well as providing resources for the nanosat community, for the hobbyists and educational communities out there to really lower the entry barriers of entry into this field. So getting right into the basics, principles of electrospray, conceptually, it's a very simple type of system. You have a liquid fuel that is either actively or passively fed through some capillary or porous structure. You have a high voltage that's applied between the emitter and the extractor. And at high enough field strengths, liquid Taylor cones form at the end of these pores and capillaries. And from the tips of these cones, ions and droplets are pulled out and accelerated through the extractor aperture to generate thrust. Now there's a bunch of different types of electrospray propulsion systems out there, and I'll just really focus on ionic liquid ion source, or ILIS. So these types of thrusters utilize a room temperature molten ionic salt fuel, typically either EMI BF4 or EMI IM are pretty typical and common fuels. One of the unique things about this type of ion propulsion is that no neutralizer is required. Due to the chemistry composition of the fuel, you can actually extract both positive and negative ions, which allows you to do self-neutralizing beams as opposed to using an electron source. In addition, no heaters are required, unlike some other types of electrospray like FEET, which uses liquid metal fuel, which allows the efficiency of these particular types of ion thrusters to be very high. They cover a very wide range of ISP depending on the emission mode, so anything from less than 800 seconds to more than 5,000 seconds at moderate to quite high thrust to power ratios, anywhere from around 14 micronewtons per watt to about 57 micronewtons per watt that's been recently demonstrated in the market. There's a few different types of emission modes. Colloidal, which droplets are emitted, which translates to high thrust and low ISP. You have mixed mode operation, in which both droplets and ions are emitted, and the pure ionic regime, which is the highest efficiency mode, where purely ions are emitted from the thruster, which signifies low thrust but very high ISP. In addition, there's a bunch of different types of emitters used in this technology. The most commonly explored and oldest types are the MEMS silicon-etched hollow capillary arrays, as well as laser ablation micromachined porous glass spike arrays. However, in recent years, there's been a lot of growing interest in macro scale CNC machined spikes or ridges to really reduce the cost and make this technology more affordable and accessible. So what are some of the advantages of electrospray propulsion at the PocketQube level? Really, if you look at the whole field, there's only a few types of EP technologies that can scale in terms of size, power, performance, and non-pressurized refuel requirements at the PocketQube level. These include pulse thrusters like pulse plasma thrusters and vacuum arc thrusters. MEMS resisto jets are up there, as well as ILIS. So all these types of thrusters have been or are being currently explored in the PocketQube realm. Of the types of thrusters available at this scale, ILIS has been able to demonstrate that it has really the highest combination of thrust to power and ISP levels at this scale. Another benefit is that they have less EMI than pulsed systems, which typically operate with very large current pulses to generate the plasma, since these operate in more quasi-DC state. They're passively fed fuel, so no heaters or neutralizers are required. And the fuel is stable and safe across a very wide temperature range and is vacuum compatible and with negligible vapor pressures at high vacuum. Because of the physics of the thruster, you can get extreme miniaturization, everything from single microscopic emitters to large emitter arrays. So this lends itself very well for all applications ranging from primary propulsion to attitude control. And depending on how the thruster system is designed, you can get a wide performance range, ranging from low thrust to high ISP to high thrust and low ISP. So here is the current iteration of the electrospray thruster that I'm developing. This is the AIS ILLUS-1. This is currently the V6 system. So everything you see here is included: the high voltage electronics, the low voltage control, the actual thruster itself, as well as the fuel, which is stored inside. So some specifications of the currently tested V6 prototype. Relatively compact in terms of ion propulsion. It's a 45 by 45 by 16 millimeters. The dry mass is 39 grams of the 1 gram fuel capacity. I'm using a very classic EMI BF4 fuel. The emitter selected was a CNC machined glass ridge emitter, which allowed me a lot of surface area to explore emission while significantly reducing the cost and making it easier to work with. So far, the nominal thrust has been measured at around 0.04 micronewtons with a peak thrust of 0.4 micronewtons, with indirectly measured ISP in the low 4,000 seconds based on the acceleration voltages of plus or minus 5 kV during peak operation. It's also very low power with 5 volts in at less than half a watt of power. So really the core of the design and around ILLUS is the porous glass emitters. So for this particular one, this is a CNC machined ridge. The glass is standard chemistry filter frit. So this is a P4 frit, a 25 millimeter diameter disc. The ridge tip is about 0.1 millimeters with a base at 2 millimeters. This isn't really an ideal geometry for emission optimization, but it was the first one that I was able to play around with and explore in developing these thrusters. So in order to further simplify the testing and manufacturing process, I've been working a lot with 3D printed housing for this and other thrusters. So here you can see a few iterations of the thruster. I did try 2 types of 3D printed plastics. The SLA resin prints here on the bottom on the left, and then the FDM Ultim 1010 on the top and on the right. The SLA stuff actually had a lot of issues with arc flashovers and discharge at high vacuum due to the outgassing. But the Ultim has performed extremely well, and there hasn't been any issues in terms of outgassing or high voltage flashovers during operation. So fueling this type of thruster is actually quite simple, but it does require high vacuum fueling. And there are several reasons for having to fuel this type of thruster and other types of electrospray thrusters in high vacuum. For ILLUS, you need to completely saturate the porous glass. So this allows the liquid to fully saturate into the pores because this is actually a quite viscous liquid. It allows for fuel degassing as well as porous gas degassing and baking out and desorption of water from the fuel just because the fuel can be hygroscopic. So this ultimately improves thruster operation because if you don't want any air bubbles or water vapor kind of bursting out during operation, which can happen if it's not properly prepared and baked out for operation. So in order to qualify this thruster, there's been significant work done on the electronics. I started out at very first with absolutely no switching on board, just applying single high voltage and working from there and looking at various semiconductor switching. And at this point, I've settled upon a high voltage micro relay, which is used to both isolate and switch the plus and minus 3.5 kV power supplies, which you can see kind of in the center here, the Pico supplies, as well as developed a simple high voltage test load for actually testing and qualifying the thruster before actual firing and vacuum. So here you can actually kind of see one of the bench tests that was done before the very first firing test to qualify the thruster electronics. So you can see here it is switching at plus or minus 3.5 kV, kind of stress testing it at higher frequency levels than would be seen in testing, just to make sure the electronics all qualify and check out. So one of the big things that have been done during this development phase, because the ridge machining takes about a few months, 3 to 4 months, one of the easy ways to optimize performance based on the materials I have is changing out the extractor. And there's been a lot of work to optimize the extractor performance. On the left, you can see a standard linear slit extractor. So this was the first one tried, and it was found that early on in testing, there's significant field enhancement right at the corner of the ridge, which would cause excessive emission and premature failure at this point. So the newest iterations actually use a special flared extractor, which reduces the field strength at the corner and eliminates emission here, and focusing the emission in the central region of the thruster to allow better performance. And again, with the extractor, it can also look at the slit widths as well as thickness. And ideally, I want as high of a field strength at the tip as possible, as well as reducing the beam divergence of the system, so that ways you get higher thrust efficiency, because the more the beam diverges, the more thrust you are losing in the radial direction instead of the axial direction. So in the most recent version, I have a very close emitter with a thicker plate that gives me better field or tighter field divergence on the beam, which you'll actually see in the next upcoming videos, kind of a comparison of the two. So this is kind of the comparison. On the left side, you have the version 5 thruster. So where you have the standard slit, which is about 0.75 millimeters and a 0 millimeter spacing between the emitter and the extractor. And on the right, you have the enhanced extractor currently used in the V6 version. So this is a 0.5 millimeter slit with the flared ends, as well as a 0.1 millimeter distance to help prevent liquid bridging and shorting between the emitter and the extractor. So here you'll actually see a video of the thruster firing. This is with the V5 design. So this is the standard linear slit. So you can actually see the ion beam firing, and right there is the transition between a positive and negative high voltage cycle. So you can see it's a very wide diverging beam, which is not ideal, and that emission is really occurring in one place. So that was kind of the reason to move to the enhanced extractor. You'll also know there's a bit of board flashes here and there during this test, which was completely resolved by adding a few surge protection resistors in the high voltage circuitry, which significantly helps stability. So again, looking at the beam, we have a very wide diverging plume, and looking at the thruster afterwards, you can actually see emission occurs exactly in the corner, with some liquid creep failure that eventually causes the thruster to short. One of the interesting challenges with ILLIS is that the high voltage tends to draw the liquid up in very unexpected ways. So you often see in post-test analysis, there's this kind of branching structure shorting between the emitter and the extractor. So moving on, we have the most recent test, the V6 test, with the enhanced slit extractor. So here you actually see now a very much tighter sheet-like beam. So you can see kind of 3 points of emission. So this was actually the first test where multi-site emission occurred in the thruster. So we have emission now across the slit. And although this beam is physically less bright than the prior beam, it put out 2.5 times more beam current. So this was at around 5 microamps measured beam current in the Faraday cup, whereas the prior test was only about 2 microamps of beam current. So again, looking at the beam, we have a very tight focused sheet-like beam. It's a little bit diverging upwards due to probably some misalignment between the optics of the emitter and the extractor. And we can see, looking at the thruster afterwards at the end of life testing, that emission does occur right in the center of the emitter, which is where we want it. And you can also see some of the liquid bridging failure that occurred during testing. So moving forward, the V7 iteration, which is probably going to be the final iteration of this particular development phase, I'm looking at new housing to limit direct paths between the emitter and the extractor, as well as employing a special shield electrode to prevent liquid creep coming up from the base part of the porous emitter disc during peak operation. So actually, these parts literally just came in last night. You can see the new 3D printed housing and the new shield electrode, and you can see one of the ridge emitters installed for fit checking. So I will actually be running this test probably within the next week and gathering data on this new geometry. Moving forward, we have the next development phase, the AIS ILLUS 1.2. So this uses the same linear ridge geometry, except with a much tighter and narrower ridge. Unfortunately, the ridge that I'm using now is a bit too wide, so the field enhancement isn't really enough to get full beam turn on and as high emission as I'm expecting. But hopefully this will be mitigated moving forward with this new design. And you can kind of see the general structure of the thruster. You have the outer casing, you have the emitter, you have a porous glass reservoir, which is a different porosity that's pushed up against the emitter disc, as well as a contact disc, and then a wave spring that goes on the bottom of here that both mechanically compresses everything as well as provides electrical connection to the board. Finally, the ultimate direction moving forward for this thruster system will be starting with the AIS ILLUS 2. So this will actually employ a full 2D array of CNC machine spikes. So this allows for significantly larger emission surface. It's a little bit more costly and tricky to machine, but this seems to be the general trend actually moving forward in work done in this field, offering quite high thrust and ISP levels at low powers. So really the aim specs for this thruster will be 1.6 watts at greater than 20 micronewtons of thrust. The ISP is aimed for over 3,500 seconds of ISP, which has been demonstrated already with the ILLUS 1 operating at plus or minus 5 kV. And with the new thruster, I will also be adding a second control board dedicated to the control and startup sequences of the thruster. Ion thrusters are particularly tricky to operate, and especially with this one, I had to play a lot of tricks in independently switching the high voltage supplies and the relays to keep everything within spec and to operate this thruster at such a high voltage in such a tight space. So here you can kind of see the CAD models of the CNC machine spike arrays as well as fitting into the housing. So kind of beyond this, I also work on other types of thrusters. So this is the AIS GPPT3 1C micro pulse plasma thruster. This was actually the very first fully integrated PocketQube thruster that I built. So you can actually see the thruster here as well as it firing. And this thruster, by the way, all the manufacturing files, all the data, all the test videos and test logs and everything are available for this thruster. So you could actually quite literally go and build this thruster yourself which is part of the open source initiative of all my thrusters that I do, which will be the same for the ILIS-1 once it completes its testing phase. This thruster will actually be flown on the AMSAT Genesis PocketQubes. So these already passed the vibration and integration testing. So we're currently looking at launch, hopefully sometime at the end of the year. So 2 of these thrusters will be launched aboard the Genesis NNL SATs, which will be particularly exciting if they function. And next, moving forward from that, my most recent testing has been with the AIS EPPT-1 micropulse plasma thruster. So this is taking lessons learned from the prior thrusters, pulse plasma thrusters, and improving performance. So I recently completed the second ignition testing in the past couple of weeks, and I have new parts in to improve performance. So the third test will actually be done in the next couple of weeks as well. Finally, there's a bunch of other thrusters currently in development, some experimental stuff that are already under initial design. So I'm looking at a solid iodine fueled microresistor jet, the first AIS vacuum arc thruster, the VAT-1, as well as a couple of experimental pulsed ion thrusters, the vacuum arc ion thruster, or VATE-1, and a pulsed plasma ion thruster conversion from the EPPT-1 to the EPPIT-1. So thank you for listening to this presentation. You can follow everything that I do on the AIS Twitter and Instagram and YouTube. I do live testing of all the tests, and you can really see the entire design process from initial conceptual CAD models to the full testing and end-of-life qualification. So it really gives people an opportunity to see how these systems are designed and developed and built from scratch. And at the end of each design cycle, I release everything open source so people can access these technologies more easily.
That was great, Michael. Thanks for sharing. Does anybody have any questions for Michael? Okay, I think we'll take that as we're moving on. Thanks, Michael. So now we're moving on to Breakthrough Starshots presentations. So we've got James here with us now. James, are you ready to share your screen?
Yes, I am. Let me.
Hello.
Hello. I like that you didn't try to pronounce my last name. So just for all of you who are expecting Pete Klupar, my colleague, to be giving this presentation, I'm afraid he had a conflict and asked me to step in. I think some of you probably saw his talk at last year's PocketQube workshop. So I don't want to spend too much time going over the same ground, but I will spend a minute or two just introducing some of you who might not know to the Breakthrough Initiatives. So hang on here. Breakthrough Initiatives were founded in 2015 by Silicon Valley entrepreneur and investor Yuri Milner, pictured there on the left. They were founded with Stephen Hawking, who was our science advisor while he was still alive. And they seek to kind of answer some of the most fundamental questions about kind of life in the universe. And these are the three major questions. Is there other life in the universe? Is it intelligent? And finally, can we visit it? So to answer the first question, we have an initiative called Breakthrough Watch, which is a sort of traditional-ish astronomy program seeking to characterize exoplanets around the nearest stars, particularly focused on Alpha Centauri. We've had instruments on the VLT, which are trying to directly image exoplanets around Alpha Centauri in the infrared, using a coronagraph and a number of other novel techniques. We are currently building a small satellite mission, well, a 6U astrometry mission to try to determine the mass of a potential planet around in the Alpha Centauri system. And so that's kind of to try and understand what our nearest sort of stellar neighborhood is like. We're very lucky that Alpha Centauri, while a binary system, is actually a couple of sun-like stars, so it is possible that there is an Earth analog there. Breakthrough Listen is trying to answer the second question about whether life might be intelligent elsewhere in the universe. It is a revived SETI search. We are monitoring the nearest 1,000 stars with time on some of the biggest telescopes, radio telescopes in the world, and have started also moving into the optical wavelength. As our own technology develops, we realize that increasingly alien civilizations may communicate using different wavelengths. This is run out of UC Berkeley, and we have a team of about 14 scientists working full time on it. And then finally, the project that I work on, Breakthrough Starshot, is meant to answer that third question. You know, if we find a habitable planet, if we think that there's life somewhere nearby, is there any way that we could reach it physically? So could we travel between the stars, and can we do it in a sort of human time frame rather than the 70,000 years that it's going to take the voyagers to reach our nearest stars? Starshot objectives, therefore, are to send the spacecraft to a star with a planet in the habitable zone within 5 parsecs, to take science data and to send that data back to Earth, to launch within 30 years and to go fast. So, and by fast, we mean about 1/5 of the speed of light, which would cover that distance in about 20 years. Now, you probably are all familiar with the rocket equation and what we call the sort of tyranny of the rocket equation, that the faster you want to go, the more mass you have to take with you in fuel, and that rapidly becomes an impossible prospect. So the final velocities that we're looking at, sort of near relativistic speeds, you would need a specific impulse of a million. Now, to put that in context, regular hydrazine rockets get about 200. Shuttle got about 250. So there's virtually no way that that traditional rocketry is going to get us to the velocities we need. It turns out actually that you would need to take the mass of about all the stars in the galaxy in fuel to get to those kinds of velocities. So there are several strategies to overcome this problem. You can either obviously raise your power, which is what I described, or reduce your weight. And different vehicles have used different kind of different versions of this. So airplanes and cars obviously keep their power and their propellant on board. Regular spacecraft, the power is external, but they have propellant on board. And for our approach, we are trying to leave both the power and the propellant behind, using a laser-driven light sail approach. So we have a concept for an enormous several kilometer in diameter laser that we call the photon engine, because it's an engine made of light essentially, and then an ultra thin, ultra lightweight sail membrane that would be accelerated using photon pressure. This is an artist's concept of what they might look like, riddled with holes from the interplanetary medium, or the interstellar medium. This is a sort of diagram of what the whole mission looks like. You'd have a mothership that would deploy these sailcraft. They would be accelerated over about 10 minutes by this 100 gigawatt laser, and and then it would then cruise for 20 years before sending science data back to Earth. But it turns out even 100 gigawatts isn't enough for a conventional spacecraft. It wouldn't give us the velocities that we need if we were sending even a CubeSat. And so our one of the main things about our solution to go fast is that we have to take the lowest possible mass, which means reducing the payload to essentially a single chip. Now, there are trends in electronics and photonics that actually look very promising and we believe are going to help us get there. You're all obviously familiar with Moore's law, and this logarithmic plot shows just how much cheaper computation has become over the last 100 years, and continues to get smaller and cheaper year by year. So this is one of the an iteration of a ChipSat produced by Zach Manchester at Cornell and launched by NASA, Cornell, and Stanford, I think early last year. And I think Zach may have given the presentation on this last year. So this is a simple transmitter, kind of like a Sputnik that they launched just to prove that we could actually track and communicate with these tiny spacecraft. Our next iteration will be much smaller than that even, but this mock-up kind of shows that you could fit all of the components that we might need on a functioning spacecraft into an extremely small surface area and mass. And now, to put this in context, it's not that much smaller than the chip in an Apple Watch, and you know, we all know that that's a very functional piece of computation equipment, right? So in the context of what's going on in consumer electronics, this doesn't actually seem that outlandish to us. Again, this slide illustrates just how much we've progressed in 20 years, going from sort of 84 grams. We can now fit all of those components theoretically into about 1/3 of a gram. This is a crude representation of what you might look like, and it's sort of the first thing that many people think of is that you would just attach your spacecraft, this little chip, to a sail. But in fact, partly because of the 60,000 Gs that the spacecraft will experience during acceleration, you don't really want differential mass across the thing. You want the mass density to be pretty much uniform, and so it's likely that we will use some slightly more novel or have to leverage sort of novel technology going forward. And so while today we're looking at these tiny chips, we may end up going towards sort of these flexible laminates, or even utilizing the developments that are being made in photonic chips, which are computationally much less power hungry than classic electronic chips. And the spacecraft may actually be distributed across the entire sail, rather than being a sort of separate payload component. So in the light of that, we're about to release our interstellar communications RFP. So the Interstellar Communications Challenge is the third leg of our sort of technology development program. The first being the giant laser, the phased array photon engine. The second is a materials challenge, materials and stability really, to try and develop the ultra high, the ultra reflective, extremely lightweight, sturdy sail membrane. And then this last one is really what I think of as our payload challenge, although we're focused on communications because that seems like the biggest problem in this, is that with extremely low power and very small mass and size, how do you transmit useful data over 4 light years across the interstellar medium with interference from the star that you're right in the vicinity of? And for everyone here, it might be that the second one is the most interesting, the onboard transmitter itself. So here we're interested in subsystem components that can meet the size, weight, and power requirements of the transmitter, but are also interested in various other components that can do sensing and the other important functioning parts of any kind of spacecraft, but on this incredibly small scale. So hopefully we'll be this is $1 to $2 million in basic research grants, probably in the $100,000 to $150,000 range for a year, and I hope we'll be launching this towards the end of the year. So so stay tuned or send me an email if you're interested. Now, before we go on, I just want to say that I don't necessarily think that chipsats are a sort of logical conclusion to the miniaturization of spacecraft. I think there are useful things that can be done at various sizes and masses, and that you shouldn't necessarily think that that the logical conclusion of the small sat revolution is to finally make our way down to chipsats. And this set of slides is borrowed from Professor Hunter Adams at Cornell, in which he sort of outlines his view of where chipsats really are useful and where they might not be. So rather than being, as he says, an incremental improvement upon conventional spacecraft, they're a sort of fundamentally different type of spacecraft. And he uses, I think, a very neat analogy from evolutionary biology about R and K selection. So here, if your goal is to make sure that enough offspring survive to reproduce to the next generation, there are 2 different approaches. There's K selection, which is used by most large mammals like humans, and many birds and other animals like that, where you produce relatively few offspring, and then you spend a lot of time trying to make sure that they survive. And it's well suited to stable environments where long lifespans and low mortality rates allow you to put that kind of energy into keeping your offspring alive. Our selection, on the other hand, applies to a different set of animals like rodents and insects and octopuses. And here you produce large quantities of offspring, and you basically spend no effort at all. You know, an octopus will produce something like 500,000 eggs, just a tiny fraction of which will survive. And that's much better suited for unstable environments and where things have shorter lifespans and higher mortality rates. And so basically, if there's a high probability that your offspring won't survive, you produce as many of them as possible. Now, if you, I think quite cleverly, he proposes that the spacecraft, this paradigm kind of applies to spacecraft as well. So in the case selection, we have what we've always done for regular spacecraft. So you spend all the engineering and money you can on making sure that your one exquisite satellite does not fail. And it's extremely expensive and extremely time consuming. And our selection would be the ChipSat approach, where you now can say, produce almost an infinite number of these. They're perfectly replaceable, extremely cheap. And you can overcome the high probability of spacecraft failure just by producing and launching many more of them. And this, of course, is well suited for unstable environments, and where if a system failure might disable an entire huge satellite, it's much less of a problem if you lose a third of your 1,000 or 10,000 microsatellites. Historically, of course, we could only do case selection, but the advances in computation and miniaturization have allowed us to move into this R selection world potentially for spacecraft. Now, as I said, if you think about when you want to use ChipSats, you want to do it when you want to produce large quantities of spacecraft and devote as little as time as possible to making sure that they're perfect. So it's good, obviously, for hobbyists, students, people who are looking for a low barrier to entry, but it's also particularly well suited for unstable environments. So places where it would be risky to send a $100 million spacecraft. I mean, there are other obvious benefits. Potentially having distributed measurements gives you access to highest spatial resolution. And planetary surfaces and very low orbit science missions can be accessed easily by littering atmospheres and planetary surfaces with ChipSats, which could take measurements across a large a large surface area. There are also ideas of using them for health monitoring, and of course you could do large artificial aperture searches for gravity waves and things like that. So there are interesting kind of potential uses of these. Now, Mason Peck, who was the former NASA chief technologist and then a professor at Cornell, and sort of the father of the ChipSat concept, I guess, points out that that subsystem technology is basically already available. We don't have to push. This is one of the great things about this. We don't really have to push for push microfabrication boundaries. That's happening already in a whole bunch of consumer industries. What we really need, I would posit, is we need testing and experimentation. We haven't, I don't think, found the killer app yet, and we need just to get more and more people access to this technology and to flying it. Of course, this is where it gets difficult because there are major regulatory issues when it comes to ChipSats. The FCC considers them too small to track, even if this is untrue, because you can stick an antenna on them, which makes them light up to any kind of tracker. But the FCC is not exactly a home to a suite of technically capable people. It is America's communications regulatory body that has taken on this role of regulating space debris in a very strange bit of a regulatory creep. So they haven't even really figured out how to deal with hundreds of small satellites being launched every year. They're much more used to sort of a dozen large satellites. And so how they're ever going to get their head around tracking hundreds or thousands of ChipSats is a really worrying problem. They've basically taken an adversarial approach. It's hard. I think it's harmed the CubeSat revolution, and it certainly has the potential to kill the sort of nascent ChipSat revolution. The decisions are arbitrary. You basically have to make your case to a particular person, and that who may change. It's really a mess. So how do we get around this problem? For now, sometimes you can do missions directly with NASA who don't have to apply with the FCC. That's how those sprites got launched. But we have an exciting opportunity coming up that might be a great showcase of what ChipSats can do. I don't know if some of you saw this article in the New York Times a couple of weeks ago about a theory that there may be signs of life on Venus in the clouds. This was published based on a paper published by Professor Seeger and a colleague at Harvard, who have taken 2 different readings that indicate that there's phosphine in the upper atmosphere of Venus. Now, phosphine is a gas that can be produced, in the enormous pressures of the atmosphere of Jupiter, for instance. But at least according to our models, a much smaller planet like Venus shouldn't really be able to produce this gas without some sort of biological process. So we have given them a $300,000 grant to look into this further and to come up with a mission concept. So we've just started this work. We're looking for, it's a sort of hypothesis-driven mission. We're going to try to understand what we can do to sample the atmosphere and to detect signs of life. And we'd like to do it like everything. We'd like to do it innovatively and cheaply. So there are 3 different sort of types of missions we can do: the large-scale, classic NASA-style missions, a medium-scale one where we might deploy something in a balloon in the atmosphere for some amount of time, or even a small one where we send a drop package with potentially sort of hundreds of ChipSats that might be deployed and be able to take in-situ measurements as they descend through the atmosphere. Some people have actually already looked at this. This is a paper by Salvatore Vivenzio, Dan Fries, and Chris Welch, which looked into the potential of using ChipSats on Venus. And even an unmodified ChipSat, it turns out, would have a 90-second hang time in the temperate zones in Venus, which could be improved. So even that would give us really interesting and fascinating data on in an extremely unstable environment. So the ideal sort of place to use ChipSats. Here is a list of potential payloads. We can do pressure detections easily, temperature detections. You can even now do single chemical detections on a chip. There are hardware accessories that you can attach to your smartphone that can detect for specific chemicals. So I think the possibilities here are pretty endless and exciting. And I encourage anyone here who's interested in this kind of miniaturization to reach out or to think about what kinds of sensors we could use to do a really exciting mission in Venus. So I think that's my time, and thanks very much for listening.
Has anyone got any questions? Okay, James, thanks very much for your time today. The presentation was
Thank you very much, guys.
So we'll now be moving on to Jose Antonio's speech, which will be about additive manufacturing in the PocketQube sort of field. So, Antonio, are you there?
Yes, hello. Can you hear me?
Yeah, we can hear you okay.
Can you see my presentation as well?
Yep, all good to go.
Okay. You're watching it full screen as well? Yeah. Okay. First of all, thanks to everyone in Alba Orbital for inviting us to this presentation. Yeah, we've been working, I would say it's almost 1 year that we've been working with them in order to develop the Alba pod. And it's been a really cool experience. Yeah. A lot of things that we have learned from both of our companies and from this product. You can see this really cool picture about the Alba pod when it was on the testing phase. Well, let me present my company. Company is CRP. It's a group of company actually made of 4 different companies, which they do kind of complementary things, except for Energica that you will see at the last. CRP Mechanica is a company specialized in CNC machining, precision CNC machining, doing really good job on aluminum and titanium parts. More than 50 years in experience on this field. Then we have CRP technology, which is 25 years experience on 3D printing, especially on SLS technology and with their own materials, which are WinForm. CRP USA, which is a sister company of CRP technology, but based in the US to serve the North American market. And finally, it's a spin-off from the company, from our background on motorsports and motorcycles. We launched almost 10 years ago Energica, which is now a full manufacturer of electrical motorcycles. We are based in an area in Italy which is more known for motorsports than for aerospace or satellites. You've probably been to Modena, you've been to Ferrari or Lamborghini or Maserati or Pagani or any other of those companies which we work with for years, and that they have helped us to develop our expertise. Also, our sister company, CRP USA, is based on Mooresville, North Carolina, near to all NASCAR manufacturers. The industries that we work mainly, it's motorsports, but as some might say, a Formula One car is just a plane upside down. So that's our link with aerospace, especially with planes, and then with satellites and everything that flies. So it's a very near expertise that we have developed in motorsport that we can apply also in aerospace. Our background, we started in 1970s with high precision CNC machining for the motorsports industry. And in the mid 90s, we bought the first SLS machine in Italy in the same time as Fiat Centro Ricerche. And we started developing not only 3D printing parts, but also start working on how to improve the materials that were actually in the market at that time, and start developing our own range of materials. It was only in 2005 when we developed this line of materials, this family of materials, which is called WinForm, especially WinForm XT, which is a carbon fiber reinforced polyamide, which is really, really good material for structural applications. In WinForm 2015, we update our WinForm material with higher strength and higher rigidity in order to improve the applications that we were already working with. It considered that XT was the first carbon film material for SLS technology ever developed. Just to give you a short story about the name, WinForm is, we started working on wind tunnel structures, developing wind tunnel mock-ups like the one you see in the picture. And that's where the name of the material came from, WinForm, the form of the wind. And we started doing a rapid prototyping for the wind tunnel. Now with the improvement of 3D printing and the materials, now we don't say anymore that we're doing rapid prototyping, but we are doing additive manufacturing, which is a whole new technology to do functional parts and not just parts that can be kind of what you expect from traditional technologies, but are fully functional parts. Our facility our production facility in Italy is based on 10 sinter stations that which we develop 3D printed parts for all our clients. We have 3 large frame machines with a printing frame, which is around 500 millimeters per side to form a cube. This is the maximum dimensions we can print monolithical parts. We can also print bigger parts, but doing structural bonding over these. We have 6 small medium frame machines and 1 small frame machine which we use to develop our materials. In the USA, we have 5 other sinter stations, which are 4 small medium frame machines and 1 large frame machine. As I told you before, we have developed our own materials for SLS technology. I'm going to give you just a brief presentation about these materials. You can find everything else I'm not telling you on winform.com, which is our website. You can download all the data sheets, some testings we have done, some certifications from NASA and ESA for the outgassing as well. Well, just to tell you, this is our top line materials. WinForm XT is our most rigid material. Just to give you some ideas, it's a very low density material. The HDT, heat deflection temperature, is around 173 degrees. The tensile strength on the x-axis of this material is around 84 megapascal, and it has a low elongation to break of almost 4%. On the other side, we have WinForm SP. Sorry, down. We have WinForm SP. It's kind of the same as WinForm XT. It's the polyamide that changes and gives a bit more of elasticity. So you can see the elongation to break increases. And this elasticity also gives more isotropy to the material, which is something that 3D printed parts have issues with. Also, the temperature this material receives without, let's say, losing the mechanical performance of the material, it's a bit higher. It's around 186 degrees. On the right side, you have our top line glass filled materials, which are WinForm GT, which, well, different to the carbon fiber materials. The mechanical properties are reduced, but you have some advantages, like the non-conductiveness of glass materials, and well, these materials also perform very well on the mechanical side. So you can see the tensile strength is for the GT is 56 megapascal on the x-axis, and 60 megapascal for WinForm LX on the x-axis. Also, the finishing of these materials, as you can see in the pictures I will be presenting further on, the material is very, very smooth thanks to a manual finishing we have developed on our own, and this gives a very aesthetic finishing. We have also developed a line of flame retardant materials, which are WinForm FR1, which is a carbon filled material, and WinForm FR2, which is a glass filled material. I'm going a bit fast over this part because you can find all this information as well on our WinForm website. Why using WinForm? Well, because it's the first carbon fiber filled SLS material ever. It's the best tensile strength material per unit in the market. It has high resistance to temperatures. A very important thing is that we have developed lots of certifications. As I was saying before, we have NASA and ESA approval for outgassing, and we have done several launches with different satellites and satellite components on manufactured with our materials. Well, this is what we have developed with the ALBA Orbital, the ALBA pod. This is the case and the ejection door, which was a very tricky component we have printed with a very thick surface in order to reduce drastically the weight of the part. Also, as you can see, we have developed a version for a space qualified PocketQube deployer. It was done using our laser sintering technology and our WinForm XT2 material. You can see some pictures of the mounting of the ALBA pod from ALBA Orbital guys. You can find the full case study also in our website. This is another case study on a pure PocketQube, which was completely developed using our laser sintering technology and WinForm XT 2.0. It was a PocketQube that contained electronics of a camera and a radio system on it. It was developed by our partner company, CRP USA, for an American client. At the end, we printed 4 of these PocketQube, which were launched into space, and it was very versatile design. This is also a CubeSat form factor. It was developed for the LISA project on Créteil University on Paris. It was a very complex structure in order to reduce the weight and to perform, as well as aluminum structure that they had developed on the first prototype. These are some case studies developed from previous projects. This is the 2-pod, which was also a pod for different satellites, different CubeSats. It served as a single structure and also for a support structure for all the electronics and for all the devices attached to the structure. It was launched from the International Space Station directly. Instead, this is the KaiSat-2. It was the first CubeSat we developed. It was developed with the University of Kentucky and Moorhead State University. It was used to launch some optics to take pictures of the Earth. This is another project we developed. It was AMS. It was a study to see if it can be a propulsion system could be developed on using additive manufacturing technologies. The good thing about this project was that it helped reduce drastically the weight of the theoretical application, because it was done on a single printed part, instead of having different components using aluminum, titanium, or other metal components that increase the weight of the part. In this case, the part was 3D printed. It contained the fuel in the inside. There were several valves attached to it, and the propulsion lasts 16 seconds, which was the target to be obtained about this project. Finally, just to give you some other applications, this is a project we did with Leonardo. It was the gallery model, mock-up, for testing all the wind tunnel applications of the AW609 model. It's a tilt rotor airplane. And some other applications that you can see. This is a Tundra Hexadrone. It's a UAV. It's used for filming and for security purposes. It was done with a mix of different materials, using WinForm XT for the arms and WinForm SP for the body of the part. And this way, the mixing the rigidity of the arms with the WinForm XT 2.0 with the elasticity of the WinForm SPE granted the possibility of landing and taking off and suffering from different G-forces, in this case related to the drone movement. Well, this is all. Thanks you for your kind attention. Hope you find this presentation interesting. If you need more information, you can contact me. These are my contacts. Or you can go into our website, www.winform.com or crptechnology.com. Thanks.
So has anyone got any questions for Antonio? CRP Technology have a virtual booth on the website. If you'd like to go check out some of our case studies, this includes their website. You could also go and talk to Antonio if you're interested in doing anything with WinForm. He's your guy. So next we've got Khalid Al-Rashid from Heriot-Watt University. He'll be talking about planar end-fire satellite antennas.
Yes, thank you. I will share my screen right now. One moment. Okay. Can you see it?
Yeah, we can see.
Okay, perfect. Yes, my name is Khalid Rashid, and I'm a PhD student in the University of Edinburgh. And thank you for the organizer, the ALBA Orbit, for inviting us to present our work. And thank you for the audience. Today, I will present the planar end-fire antenna designing using substrate integrated waveguide technology for picosatellite and other small satellites. Starting, I will give an overview about this project or this presentation. At the first, I will divide the background and the problem statement of this project. Then I will move to state the objective. Then after that, I will show you the antenna structure overview and where is the antenna will radiate in the Cube satellite. And after that, I will present the part of this antennas and the function of every part. And also I will move to the simulation results by presenting two versions of our simulation. Then I will finally mention some conclusion and future work. In my opinion, I think the best way to give the background or like the problem statement, it's how we achieve the end-fire pattern and why we achieve that. In the last 20 years, the satellite industry start to grow up, and especially the small satellite. And in the last 5 years, there is an exponentially increase in the Cube satellite. And in my area or our area of the team that I'm working on, and the antenna and communication stuff, and by stating the downlink for the LEO Cube satellite, and it was 18 gigahertz. And for the limitation for this CubeSat, we introduced that we will use the SIW because it will technology, because it will provide us with low weight and with the easy to integrate and also with the low cost. And to increase the novelty of this antenna, we introduced the leaky wave. And after that, in the next slide, I will mention why we exactly mention the end-fire pattern. It's the use of pointing toward the ground station, and it will have the power efficiency when the antenna, when the CubeSat goes, and as we know that the LEO orbit, it goes around the Earth exactly from 4 to 5 passes. It depends about the way of this CubeSat, and it will be the antenna. It will radiate from this at the end of this cube So it will radiate toward the end fire, and it will be toward the ground station. And the objective of this project is to design an antenna that works in the space environment, absolutely, because we are working in the satellite area, and to design an end fire to achieve the high directivity toward the ground station, and also the power efficiency, because working in a space environment, the power, it's always like a limit. So we need to find a way to work with it in a specific and in a smart way, and also to have an antenna that survives from launching. As we know, the amount of vibration in the launch, it will affect the antenna. So if you have an antenna that have complicated or like not a rigid to your satellite, it might break at the launch. Then also we need to meet the requirement for the weights and the size for these kind of CubeSat antenna. And at the end, we need to achieve the design to be easy to integrate, lower complexity in terms of the mechanical part, and also lower the cost and the profile. This slide will present at the left side, will show you the layer of this antenna, and it's, as we can see, the crown as the bottom of this antenna. Then we can see the substrate that we are using, and also we can see that here that the energy leaking from the substrate integrated waveguide going to the grounded slab, as I will explain in the upcoming slide, and to radiate toward the end fire. And also we can see that the top bottom can be divided by two parts. The first, it will be in the parallel plate and also the SIW, and the second part will be the sub-wavelength batches. And we can see that the waves here, or the E field, need to be a uniform, and I will discuss it in the upcoming slide. This slide shows you that the structure or the top of the antenna, and also we can divide this antenna to three parts. The first part is the leaky substrate integrated waveguide, and it's that part here. And the second part, it's the matching bar to smoothly have the power coupled with to the surface wave in the part 3. The first step, we need to design the T-junction, the conventional T-junction, and this useful to divide the power along the aperture equally. And also to add a point, we need to add an inductive in the center of this parallel plate and the middle of the SIW to reduce the high reflection to the input of our antenna. And we can see here a screenshot of the design, and we can see that the E field divided equally along the aperture of our structure. Moving to the leaky wave partially reflected surface, and to design this, first we need to make one of the T-junction walls as a lossy wall, and to achieve this we need to increase the spacing between the via and this wall to more than the ratio condition to achieve that the energy leak to the parallel plate waveguide. And this will make the power, and this is so important because it will make the power coupled with the coupled to the transfer electromagnetic wave inside this parallel plate to excite the field toward the end fire. And also to calculate the distance of this L, it will be easily after we mention or after we introduce, because we want to have the 90% efficiency launching the energy toward the matching section. So we can use it by this, using this equation. It will be the 2.3 divided by alpha. And to mention from before that we need to achieve a uniform field propagation, as you can see in the middle in this picture, that our field, it's uniformly. And to achieve that, we need to work the frequency, operation frequency, it's need to work like slightly nearby the cutoff frequency. And as we can see, when we increase the frequency, there is an introduce of an angle, and our field will divide it by 2 parts, and at the end we will not get the radiation that we want. And when we working in the down frequencies, the structure will not even start to propagate. Moving to the matching section and the grounded slab, grounded dielectric slab, and this is important to make the energy coupled from the transfer electromagnetic wave to the transfer magnetic, because this will introduce the surface wave on the GDS. And the matching, the subwave length, as we can see here, it's introduced by 2 parameters, the D and the G for the subwave length. And there is an important thing, we need to cut this parallel plate after a certain distance, and this distance need to be lambda G by 4 or multiple of that distance, because this will make the field smoothly goes toward the grounded slab. And to achieve a good radiation pattern with a low back loop and a low side loop, we need to have the beta along the structure similarly to each other. Moving to the simulation and results, at the first we achieve a quasi end fire, and as we can see in the middle picture here, the structure, the 3D pattern, and we achieve 13.4 with a main lobe direction 46, and also with a low side lobe level with a minus 13.4 in the phi cut and a 90 for the theta cut. And as we can see, to make it much easier in the 3D design. Moving to the retier list, our antenna, as I mentioned at the first, that we need to design it at 18 gigahertz at the LEO orbit downlink in the European area. And our antenna achieved 18.6 at S11 with a minus 20 dB. Then after that, we integrate our antenna, our structure, and as we can see here in this picture, we integrated with the cube, and in the 3D printing, we can see that the affecting, it's not a huge, and the radiation pattern for this antenna can achieve a 13.2, and it's not a huge difference from the gain that we achieve without the cube satellite. Then after that, to achieve a truly end fire radiation pattern, we introduce a air via. This air via will increase the load at the end of this structure, as we can see in this picture, and this air via will be just in the substrate layer, just an holes that will goes until the ground, but it will not cut the ground. It will be just until it reaches the ground, as we can see here. And this, after increasing the load here, the pattern will start to excite toward the end fire, and we increase from our first version, comparing to the first, comparing to this version by 15 degree as a main lobe direction, and we reach 16 degree in the phi cut. That's important, because it will show us the edge of the CubeSat. And also the gain increases to be a 13.7, and this is a good things to achieve a high gain in such a small structure. But for the bad thing here for this version, our side lobe, it increases to -4. And this is for the phi cut, and for the theta cut, even we increase the gain. And also it was the same as the direction of the male lobe direction. So it's show us or prove us that this antenna is a highly directive toward the earth. And the important about the end fire, as I mentioned before, and comparing to the conventional batch that having the board side radiation pattern, the end fire exactly give us a useful thing and a way to give it with a smart way radiation toward the ground station with a minimum way in changing the cube by using the reaction wheels of the cube satellite toward the ground station. And for the conclusion, to sum up with that, we achieved in the first version a quasi end fire antenna with a 13.2 gain and with a 46 as a male lobe direction, and also with a good side lobe level -13.7. And in the second version, we increased the male lobe direction to be toward the end fire to be 16 degree, with increasing also in the gain as 13.7 right now compared to our first version, but the side lobe that it's become worse to -4.3. And for the future, absolutely we will focus on the air via the structure to achieve a truly end fire pattern with a lower side lobe, and after that we will integrate it with a CubeSat and fabricate it and do the testing in the upcoming 4 months. And this reference that being used for this work. And any questions?
So this is the final talk of today. So does anyone have any questions? Okay, thank you, Khalid, for presenting today.
Thank you so much.
So this is the last of our presentations. There'll be more tomorrow, starting at 11 o'clock in the morning, EST time. If you also would like to see some of our exhibitors, they're still on the webpage, and you can arrange to talk to them for tomorrow as well. Thanks for everyone for coming out today, and hope you can all make it tomorrow as well and make it another good day full of PocketQube speeches. We'll be seeing everyone for today. Bye.